We're going to start on chapter 14 today, acids and bases. And I built a break into it so that we can finish 14 and 15 on Thursday, but hopefully we'll get through 14 today. It'll be good if we can. Then we won't be rushed on Thursday. Okay. Well, we'll start off acids and bases. Definitions of acids and bases have developed over the years. Arrhenius, you've probably seen that name before, was also working on acids and bases, and he proposed a definition that assumed that the molecule that was going into solution, into aqueous solution, contained either the hydrogen ion or an acid, right? And that's just any group, or it had a hydroxyl attached to it. So when it goes into solution, it dissociates into those two, which is actually a process of ionization. These are covalent bonds for the acid, right? This is not a covalent bond, so it's a dissociation, and this is an ionization. But under Arrhenius' definition, this would produce the that part of the molecule plus the hydroxyl. And he said this is what was the reason for acidic characteristic versus basic characteristics. And back then, you could taste your solutions. This would be sour, and this would be bitter, right? So if you take a medication that's coated and you accidentally bite it, more often than not, it'll be bitter. And that's because it's a base. So that one works for 90% of the situations where you'll find acid or base characteristics in solutions. But not long after, Bronsted and Lowry, both two separate investigators, came up to the same, offered the same modification that would also cover more acids and bases. And here's one example. There's Brandon. Acids pretty much fit the bill, right, for either Arrhenius or Bronsted and Lowry. The bases are a little trickier. Here's an example. If we take ammonia and dissolve and put it in solution, it gives basic characteristics, but there's no hydroxyl there. So where'd the hydroxyl come from? Well, Bronsted and Lowry said, when you put something in an aqueous solution, water is a reactant, right? So it reacts with water and produces this polyatomic ion plus the hydroxyl. That's where the basic characteristic comes from. So they said, rather than focus on the hydroxyl, we're just going to focus on the protons, on the hydrogen ions. And we say anything that donates a proton is an acid. So this would still be an acid under Bronsted and Lowry. This would be a base by Bronsted and Lowry's definition because it accepts a proton. Okay, where does it get its proton? From water. Right? If you look at water this way, one of these protons goes over here, and what are you left with? Right? And it doesn't take the electron with it, it leaves the electron behind. So you have the hydroxyl. That's the basic difference between Arrhenius and Bronsted and Lowry. Now, very often, when we start to conduct acid-base reactions, the Arrhenius concept works fine. But this broadens the field, and Bronsted and Lowry covers all of Arrhenius plus more. Now, there's one beyond that. I'm not sure if we're going to get to it or not. Lewis acid and base. I think we do get to that one later. Lewis acid and base even goes beyond this one and covers more ground. But just keep that in the back of your mind and we'll get to it sometime later. Eraser. All right. So when we react an acid in water, if you view the acid-base reaction from the perspective of Bronsted and Lowry, then water is actually a base because it accepts the proton. Whereas the, in this case, hydrogen chloride in aqueous solution donates the proton. And we're going to find out later that water can either be an acid or a base, depending on the context. All right. So this is an animation of, there's ammonia on your left, with a nitrogen and 3 hydrogens, and then water on the right with the oxygen and 2 hydrogens. And it's like there's a tug of war between for that proton. And eventually, or some of the ammonia accepts a proton. We're going to find out later that there are not many of these that happen. Right? If we write it, let me write it again. If we say this is the base and this is the acid, and there's an equilibrium set up in there for a transfer of proton to that ammonia, the equilibrium itself lies way this side, right? 95% or greater of the ammonia in solution is still ammonia and it has not produced ammonia. Actually, it's higher than that. I think it's over 98%. I did the calculation. And in fact, when we do the complex ion experiment, I've got a page in the back of that hard copy that proves how much of the ammonia is in this form and how much is in that form. Just as an exercise, it's not something we have to know. All right. Here we go, get a tug of war. We can also have a tug of war between water and water in solution. Now, it's even less likely for the proton to transfer from one water molecule to the other one than it is for the proton to transfer from water to ammonia. It's even less likely. So it has a much, much, much smaller equilibrium constant than this one does even. Okay. So this is what we would, when we write an acid reaction where we have the acid in water and it's an equilibrium with a transfer of actually a transfer of a proton over here leaves us with that negative ion plus 3 hydrogens with a plus charge because this one's right. We have to balance. This is neutral, minus plus, that's neutral. So, and this is what happens to protons in solution. When you put an acid in solution and one or more of the molecules transfers a proton, these protons do not exist free floating in water. It just doesn't happen. They're always transferred to something else. And in this case, we transfer to the water molecule and it makes a new polyatomic ion called a hydronium. Okay. Now, for calculation purposes, we could just as easily write this like that. And the calculation, the results that you would get from an equilibrium calculation would be exactly the same. But this is reality and this is convenience. Okay. Now, whenever a base accepts a proton, now it becomes a conjugate acid of that base. And by that we mean it's able to donate the proton. Right? It could go back the other direction. It could be an acid, but it's the conjugate of this base. And this acid gives you a conjugate base. Okay. Terminology. Now, in chemistry, well, let me back up. Most people think of strong acid, strong base as anything that'll burn you. Well, in chemistry, we have a different way of thinking of strong versus weak. Strong means that for a strong acid, the proton dissociates from the molecule almost 100%, if not 100%. That's a strong acid. So hydrochloric acid, nitric acid in solution would be considered a strong acid. Now, it may or may not be strong enough to burn you. It depends on its concentration. A weak acid would be something like acetic acid, where just a few of the hydrogen protons leave the acetic acid molecule and go to water. And they leave mostly the hydrogen acetate molecule intact. That's a weak acid where you have very little dissociation. I should use the proper term, ionization. Okay. Now, if that acetic acid is concentrated enough, then you will have sufficient protons in there to do some damage to your skin. In fact, we used to use glacial acetic acid in procedures. Glacial is another term for 100% acetic acid. And it's hazardous just because it's more concentrated. It will burn you, plus it's an organic compound, right? So you can set it on fire. It'll burn, or it'll react with some other oxidizing chemical. So that's why we don't store glacial acetic acid in the same cabinet as sulfuric or nitric acid, because sulfuric and nitric acid are oxidizing acids, and they will combine with acetic acid if bottles break, and the reaction is extremely exothermic. So we keep them separate. Okay, so that's the definition of strong acid versus weak acid. Now, when we have we'll just use it generic. Say we have a strong acid here. What does that mean? That means that most of it goes that way, right? Produces like that, right? So if it does that, how eager is this conjugate base? How eager is it to accept a proton? Not very, because it just got rid of it. It wants to get rid of that proton, so it goes that way, right? So so what I'm trying to say is strong acids make weak conjugate bases. Okay? They don't want to go back. And vice versa. If this is a weak acid, it will produce a strong conjugate base. So acetic acid, when it produces the acetate ion, it will very readily accept a proton. And that's why most of it is back over here anyway, as a weak acid. Okay, so this is the publisher's idea of explanation. A strong acid will produce, there it is. A strong acid will produce lots of hydrogen ions and lots of conjugate base. Whereas well, let's see. This is a I don't like the way they use a B here. B implies base, but use your imagination. If this is an acid, then, and it's weak, it's only going to produce a little bit of hydrogen ion and a little bit of conjugate base. Most of it is still acid, undissociated or unionized acid. Okay. All right. So this puts everything together in one place. We can, one thing we haven't discussed yet is in quantitative terms, you can write for weak acids. For strong acids, an equilibrium constant doesn't mean much. It's almost infinity, right? It's nearly all over here, right? When you have, if we were to write for a strong acid, the K, and sub A means acid ionization constant. If we were to write the expression here, it would have an A minus, hydronium, and the undissociated acid. So if this is a strong acid, that approaches zero, right? Anything divided by zero is infinity, right? So this number is extremely large or infinity, and it has very little meaning. It's useful though for weak acids, right? And you can tell how weak, just how weak the acid is by this number. If it's extremely weak, this number would be very small because this term is very small. Okay. All right. So I mentioned if you have pure water, one water molecule can approach and react with another water molecule and transfer a proton from one water molecule to make a hydroxyl, and then that transferred proton makes a hydronium ion. That's the first one. This is called autoionization. Because there's nothing else in there but water. Well, this happens with any potential proton donor acceptor. If it's pure, then it could be like ammonia, and you could get the same thing happening with ammonia here. Right there, where you transfer one of these protons over to the other one, and you get this ammonium ion plus this amine ion. And this would happen. Farmers don't think about it when they're fertilizing their crops, but if the farmer's using anhydrous ammonia, which they do very often, especially in Midwest where they're growing lots of corn and need lots of nitrogen, they have equipment that will, they have this tank of pure ammonia. It's pulling behind the tractor, and then it goes through it has to be stainless steel or corrode anything else. And it goes into these knives that go down into the ground, and they inject the ammonia underground where there's moisture, so that ammonia instantly reacts with the water, goes into solution. If you don't do that, then it just goes and it's gone. It's like dollars just floating away. But in the tank, this reaction goes on. You get a proton transfer between ammonia molecules. Self-ionization. Okay, so when we're talking about water and the reaction of water with another water molecule, right, sets up an equilibrium, and we get the hydronium ion plus the hydroxyl, right? So either one of these, take your pick. One's an acid, one's a base, conjugate acid, conjugate base. Okay. If we write the expression for this, this is a pure liquid, this is a pure liquid, this is aqueous, this is aqueous. So if we write the K for this, and it has a special subscript, KW, this is the only reaction that has that one. Then we would write what? Hydronium, hydroxyl, divided by like that, right? What's wrong with this picture? Water's pure liquid. We don't count pure liquids in equilibrium expressions. That goes out. So it's just the hydronium concentration times the hydroxyl concentration. That's it. And that value at 25 degrees, actually it's 24 degrees, but I'm not going to quibble, times 10 to the minus 14. So it's a very, very small number. Right? And the other thing to consider is, well, this is, while it is autoionization, this takes advantage of the amphoteric nature of water. Ampho means both, and teric means teric. Okay. So another thing to remember, I think I got a slide on that. Before we do that, always remember that in aqueous solution, this reaction is always happening, no matter what else you do to it. This is always going on. Now, if you put in a strong acid, of course, then the effect of the strong acid overwhelms this one, and it's insignificant. But if you put in a weak acid, a very weak acid, then maybe this one has some impact on the overall acidity or basicity of the solution. Okay. So, if this is pure water, how did we get that number? Right? The same number of water molecules here as here, right? They're equal in concentration. That means these have to be equal also. Right? So what would these values be to give you 10 times 10 to the minus 14? Excuse me. Get ahead of myself. It would have to be 1 times 10 to the minus 7 for the hydronium, and 1 times 10 to the minus 7 for the hydroxyl. That's the only way you can get that from pure water. Okay. Now, if we add some acid to it, right, these values could change. But if this one gets larger, that one has to get smaller because this one is a constant. No matter what else we do to that solution, add acid, add base, this has to be honored. Okay. For pure water, where we have equal concentrations, and we're going to interchange H plus and H30 plus, H30 plus. So if the hydrogen ion concentration, which is what we're saying here, is equal to the hydroxyl, then you have a neutral solution. Okay, that's always the case. If the hydrogen ion concentration exceeds the hydroxyl ion concentration, we've done something else besides, there's something else besides water in that solution that's affecting it. If we add an acid, say, then we would increase this one and that would decrease this one. Then you have an acidic solution, and vice versa. If the hydroxyl exceeds the concentration of hydrogen ions, then you have a basic solution. Okay. Now, I'll say this as an aside. This occurs at 24 degrees, 25 degrees. If you change the temperature, you will change that value, right? Because these concentrations will change with temperature. But that definition holds no matter what the temperature is. If you've got equal amounts of hydrogen ion concentration and hydroxyl ion concentration, it's neutral, no matter what the temperature. Okay. All right. So let's see. The equilibrium expression constant, well, it should be this one. Again, if that's a weak acid, yeah, they're flipped. Okay, and that will be the one you would use for any weak acid. If the equilibrium lies to the right, that means what? This component is very large by comparison to this one. Right? Actually, much greater than 1. And if it lies to the left, that makes this very small. And that means that the K value for any acid is going to be much, much less than 1. All right. If water is a better base than A minus, do products or reactants dominate at equilibrium? So we have to compare the two. If we have this reaction is going on, and then we have this reaction, this reaction, and I'm going to abbreviate. Right? We're going to leave water out of this for now. So if water is a better base than A minus, that means this water molecule accepts protons better than this one does. So what would that say about products or reactants dominate at equilibrium for this one? Well, if this one doesn't want to accept protons, then I would say the products would dominate. Wouldn't you? Because where is it going to get that proton? Right? It's not going to, well, it could be coming from that one, but it also could be coming from this one. Oops. Does this mean HA is strong or weak acid? Well, it should be a strong acid. Is the value of Ka greater or less than 1? It should be much, much greater. It's a strong acid. Okay. All right. Consider a 1 molar solution of hydrogen chloride or hydrochloric acid. Put these in order of strongest to weakest base. All right, so let's make some room here. So we've got water as a possibility. We've got A minus derived from a weak acid. It's a conjugate base of weak acid. Okay, and then we have Cl minus. So we know what Cl minus is. It's an extremely weak base because hydrogen chloride in water is a strong acid, hydrochloric acid. So that makes this very weak base. And this would be conjugate base of a weak acid would be a strong base. Right? And water would be in the middle. So if we're going from strongest to weakest base, the strongest base would be this one. And it would be a little stronger than water, which would be stronger than that one. Oh, I didn't realize I had slides on this one. How good is chloride as a base? Not. And A minus is a very good base. So if we put them in order, they should be in that order. Based upon strength of their strength as a base. Okay. So let's consider Na, where A minus is an anion from a weak acid. So if we put Na, sodium aide, in solution, what's going to happen? Well, when it goes into solution, actually, it's not an equilibrium. This is completely soluble. It dissociates in this one and this one. And we're also told that this would be derived from a weak acid, so it's a strong base. All right, so what about that? What does sodium do? Nothing. Sodium just goes into solution. It's hydrated, of course, right? The water molecule is polar, so the negative ends of the water molecule surround the sodium. But when the positive ends surround this strong base, it snatches some hydrogen ions from water. And that's the reaction that occurs. Right? So you get the conjugate acid would be a weak acid for this base. And the conjugate base would be actually a strong base from the weak acid water. So the conjugate acid is still going to be weak. Conjugate base is going to be strong. Right? Which way will equilibrium lie? Well, since this is a very, very strong base from a weak acid, the equilibrium is going to lie to the right. It's going to find that protons from water. Nope. That's what the creator of the slide said. So I left it in there and I just crossed it out and said, nope, they got it wrong. It lies to the right. Okay. Consider this one where is the value of KB greater than or less than 1? And we talked about Ka. How do we write Kb? Well, Kb is written like this. You put that anion in water and you set up an equilibrium with Ha plus OH. So what would Kb look like? Well, this is still pure liquid, so it's not there. So we have this one, concentration. We have the hydroxyl concentration divided by A minus. So there's your Kb. And we write these Kb's for bases like this. If we've got a base on this side, it's going to take a proton from somebody. Whereas if we write a Ka, we've got an acid here that's going to donate a proton to somebody. That's the difference between the two. So how about the value of Kb? Well, if this is a strong base, then the equilibrium is going to lie to the right and the Kb is going to be large. Not less than 1. I got several wrong in this one. Much greater than 1. Okay. Consider the same reaction. Does this mean A minus is a strong or weak base? Well, we covered that one already. It's a strong base. It's derived from a weak acid, so it's a strong conjugate base. All right. Okay. So let's take a look at acetic acid. HC2H3O2. Now, did I show you how it sometimes is written differently than that? Did I show you that one? Sometimes it's written with a more molecular bent. It's got a methyl group on this side connected to a carbon, and this carbon is connected to that carbon. And then it has a carbonyl, and an O, and then an H. This is your acid proton. Okay, sometimes you might see it that way. You don't have to write it that way for us. This is fine right here. Go. Okay. If these are both weak acids, we've got this one. What would this one be? This one would be acetic acid, right? Because it's got an oxygen in it. We don't say hydro. That one has no oxygen in it, so we say hydro. And ions become X, hydrocyanic acid. right? If it ionizes, this one ionizes, it produces the proton, and I'm shorthanding it again, right? I'm leaving the hydroniums out. Right, does that. So if this is weak, this is strong conjugate base. Okay. This one can do the same thing in aqueous solution. Leaves us with the cyanide ion, and this is also a strong conjugate base. Now, which one is stronger? And it depends on which one of these is weaker. Right? These are both weak. Acetic acid is stronger than HCN. So this is weak, but this is very weak. Okay. That means this is very strong. And that's strong. So this one produces a stronger conjugate base than that one does. Okay. All right. What they want us to do is put these in order. Weakest to strongest base. And okay. So let's bracket them in first. What's the weakest base in here? That. That's weaker than any of the other bases because it's derived from a strong acid. All right. Now, which one would be the strongest base? I'm thinking this one right here. Well, that one right there. Now we just have to say which one comes, which is goes in here, right? Water or this one. I think that water is a stronger base. No. Let's think of it this way. Which one is the stronger acid, water or acetic acid? Acetic acid, right? So water would be the stronger base. Well, hydroxyl would be the stronger base. Okay, I'm going to take a wild guess. I'm going to say, I could be wrong. Now, if we had values to go from, this would be a no-brainer. We could figure it out just like that. But here we're just trying to reason it. What? It didn't tell me. Oh, there it is. Okay. Okay, so I got it backwards. Should be like this. Now, why is it that way? Well, we're pretty certain that this one should be on that end and this one should be on this end. It's these two in the middle that give us trouble. All right, so if the kW for water is 10 to the minus 14, it's way over here to the left. And so that means that water is a weak base, a very weak base. And the Ka for acetic acid is 1 times 10 to the minus 5th, which makes it a little bit stronger acid. But the place where we get confused is we're not talking about the conjugate base of water, we're talking about water. If we were talking about the conjugate base of water, then it would be much, much stronger than this one. But when we're just comparing the water molecule plus this conjugate base, this one is a stronger conjugate base than water. Now, this value, see if I can point to it right here, the Ka for acetic acid is right there, 1.8 times 10 to the minus 5. I'm gonna show you how to calculate the Kb for C2H3O2 minus from that value. And if we have that value, then we can compare values here, 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 here. And we can do the same thing with this one. Okay. All right, let's look at this one. Let's just erase all of it. Make some room. Erase this one. What's the value of K for this reaction? So we have HCN aqueous plus F minus aqueous, and it's in equilibrium with Cn minus plus HF. Okay, and we're given values for HCN, 6.2 times 10 to the minus 10. So HCN, K of HCN is 6.2 times 10 to the minus 10. And the K for HF is 7.2 times 10 to the minus 4. Okay, so if we're going to determine what is the K for this reaction, we know how to write the expression. We say concentration of CN cyanide hydrofluoric acid times hydrofluoric acid divided by the concentration of HCN times F minus. And we know that if we use Hess's law, right, we can break this down into HCN yields Cn minus plus H plus. And the value would be 6.2 times 10 to the minus 10. And then for this one, we would have F minus plus the hydrogen ion yields HF. And that value would be the inverse of this one, wouldn't it? Like when we write an equilibrium expression, if we have this expression, but we want it, this is for HF in equilibrium with H plus and F minus. So if we just invert it, that inverts that K, doesn't it? Okay, so this one would be 1 over 7.2 times 10 to the minus 4, which would be beyond my ability to do in my head. So 7.2 exponent minus, and then we just invert that. It was 1.39 times 10 to the third. And if we add these together, we get that equation, right? Because these hydrogens cancel out. So what do we do with these K's to get the overall? It's not a trick question. Multiply. Yeah, multiply. So if we multiply these two, see that one's already in there, so I'm just going to punch in 6.2 exponent to the minus 10 times. And this is 8.6. I can only keep 2 times 10 to the minus 7. Would be the equilibrium constant for that expression. Okay, so the slides are doing it. Let's see. What was the question? Wasn't the question? Yeah, the value of K for that reaction. Okay, so we're getting a lot of extra for your dime. All these statements are true. Or it just wanted us to know overall reaction less than 1.
Yeah.
Or greater. Okay, so I gave you the exact value, but this was reasoning. Which one of these is farther to the right or farther to the left. Well, since this one is farther to the left, then this one wins out and should be negative, right? Which it is. I get carried away. Okay, now, what if we did want to calculate the KB for this ion right here? Not for this reaction, but for the inverse of the acid ionization. But for KB would be put this ion in aqueous solution and calculate the KB for that F minus reacting with water, right? We can't just invert it then. It doesn't work. It has to react with water, which is a different reaction than this. Okay, I wanted to make that point because the temptation is to just say, all right, the KB is the inverse of the KA. No, it's not. Okay, and I'll show you why in just a second. I'm gonna leave those there just in case. All right. Oh, we're going to use generics, so it doesn't matter. The other time. Let me see. Go to here. Oh, yeah. All right. I'm going to have to move. We're definitely not going to finish the chapter today. I think there were 110 slides. So it's wishful thinking that we get finished. If this is the acid dissociation producing A minus and hydrogen ions, and that's the Ka for it, then the reaction we're interested in is take that A minus, and react it with water. And how do you get that in solution? You don't put it in as the acid, because then you got the upper reaction is operating here. You take the A minus salt with some cation, right? It could be ammonium A, or it could be sodium A or potassium A, something that's soluble that doesn't react. So ammonium probably wouldn't be the best choice. Some alkali metal would work best. And that would put A minus in solution without its hydrogen ion. So if it's from a weak acid, it's going to go looking for hydrogens. It's going to find them with water. And this is the reaction for the conjugate base with water. All right. So this would be the expression for KB. Right? So what we want to look at is what's the relationship between Ka and KB. So if we know one, can we calculate the other one? Or if we know KB, can we calculate Ka for the weak acid from which it's derived? Right? As it turns out, if we add these two equations together and then we multiply Ka times Kb, correct? Just add those two equations together. Right? The HAs cancel. The A minuses cancel, right? Because they're on opposite sides of the arrow. And what do you have left? Well, you have water dissociates into hydrogen plus hydroxyl. Right? And what is that equal to? Right? Ka times Kb is equal to Kw. All right. So how do you calculate Kb from Ka? You take Ka and divide it by Kw. Well, or Kb, if you know Ka, excuse me, if you know Ka, then you divide Kw by Kb. I misspoke. As they say in Washington, D.C. So that means that to find Kb from Ka, you should divide Ka into 1 times 10 to the minus 14. Or you can go the other way. But you're still dividing the known one into 10 to the minus 14 to get the unknown. We already did this one, right? I got ahead of myself. So this is what we're doing. We're putting those two together. Right. There's that one. But we need HF inverted, so there it is. And there's the value. Then combine the two equations, and there we're canceling our value, canceling, and there we get K of that reaction is 8.6 times 10 to the minus 7. Okay. All right, pH. What do we mean by pH? There was a, I think it was a Swedish chemist. There's a lot of work going on in Scandinavia during the mid to late 19th century. Lots of work up there. And there was one guy named Sorensen. I guess I should capitalize that. Sorensen. He, to put it mildly, was just irritated having to express concentrations for his acid-base research in terms of molar values. He wanted something simpler. Right? So he proposed a mathematical transformation. And he just said, all right, if I've got something like, let's use, say it's a neutral solution, and you have 1 times 10 to the minus 7 molar hydrogen ions concentration. Right? So that would be a neutral solution. So, okay, here's what I'm going to do. I'm going to take the log of that. Right? The log of that gives you what? Well, remember when you take the log of A times B, it's the same as the log of A plus the log of B. Right? So what's the log of 1? The log of 1 is 0. Right? It's 10 to what power gives you 1? 0. Plus, what's the log of 10 to the minus 7? Well, what power of 10 gives you 10 to the minus 7? Minus 7, right? Okay. So this by itself gives you a value of minus 7. So the log of 10 to the minus 7 is minus 7. But that only partially solved the problem for him. He says, I don't like negatives either. So here's what we're going to do. We're just going to change the sign. Now, and call it pH. So pH is a logarithmic transformation, which is simply a negative log of the hydrogen ion concentration. That's it. No matter what the hydrogen ion concentration is, you can calculate this value because it's nothing but math. Okay. So this pH 7 would be a neutral solution. Now, when we're, if we have to keep track of significant figures, right, it's the nature of logarithms that the number of decimal places in the log is equal to the number of significant figures in the original number. So this one has 2 significant figures. That means this needs 2 decimal places. So it's actually plus 7.00. Okay. And if we were to go backwards, how would you do that? Well, let's pick a different pH. Let's say pH 6. Okay. How would you transform that? Well, what is it equal to? Negative log of the hydrogen ion concentrations. Okay. So we want to get the negative over on this side. Negative 6 equals the log of hydrogen ion concentration. Okay. So this value is the power of 10 that equals that value. So it would be that value. Hydrogen ion concentration is actually 10 to the minus 6, isn't it? Okay, so that's what you look for on your calculator. 10 to the x, and it's usually shift up from the log key. And if we have to use natural log some other place, it's the same thing for e to the x would be the natural log. This is called the anti-log. Transformation. So you go backwards or forwards. So this is neutral. What would this be? Well, 10 to the minus 6 concentration. Huh? Yeah, this, well, we can't say because we don't know what it's derived from. All we can say is this is given in the solution. It could be a weak, it could be a strong. But this molarity is a greater number than this one is, isn't it? Or, yeah. 10 to the minus 7, 10 to the minus 6. This is 10 times greater. Right? So this is an acidic solution. So if the pH is less than 7, it's acidic. If it's greater than 7, it would be basic. Okay. And the pH values are 1 order of magnitude apart, each one. If you go from 7 to 6, that's an order of magnitude bigger. If you go 10 to the minus, if you go pH 5, that's 2 orders of magnitude. More acid than this one. Right? That's the nature of logarithm. Okay. This is this came out straight out of your book. These are some examples of acidic, neutral, and basic solutions. We already know that ammonia is going to be basic. Right here, because we showed that earlier. Sodium hydroxide, of course, drain cleaner is going to be very basic. All right. Stomach acid in this range right here, 2. Well, if you eat a meal heavy in tomatoes, it's probably going to drop down to 1. Battery acid is around 1, right? Sulfuric acid. Vinegar is in the name between 3 and 4. Okay. Milk and blood they hover around neutral. Right? Anybody had anatomy and physiology? Remember what the normal range is for blood? pH, they give you. Yeah, you should have been exposed to pH already.
Yeah, I can't remember.
Points.
Yeah.
I think it's 7.35 to 7.45. Slightly basic. And we're going to talk about that in chapter 15. This is a buffer, actually in our blood, it's a buffer system. And it's several buffers come together to keep that here. If you go beyond that or under it, if you go more acid or more basic, then you can get into trouble in a big hurry. Diabetics, sometimes they go acid, they go ketoacidosis. Your body can't use glucose, so it derives energy from another source. And the result of that is ketones and carboxylic acids. And that drives your pH down too low. That if it gets low enough, then you better head to the hospital quick. Okay. We keep going. That was Sorensen's doing. He's going to come up again when we get to buffers. What's the pH of these solutions? Well, this one's easy. You can do this one in your head. That one, the pH would be 4. Right? pH 4 would be an acidic solution. But this one is a little bit different. If we have 0.040 molar hydroxyl, Right, how do you get the pH out of that? Well, at this point, we have to do it the hard way. I'm going to show you an easy way in a minute. But the hard way is Kw equals 1 times 10 to the minus 14, which is equal to hydrogen ions times hydroxyl ions. So all we do is insert this one in 0.040 and solve for that one. Right? So we take 10 to the minus 14 and divide it by 0.040, correct? 0.040 divided. And that's 2.5 times 10 to the minus 13. All right, so that gives us 2.5 times 10 to the minus 13 hydrogen ions. Now we can take the negative log of that. So the negative log would be that, and change the sign. Be 12.6. 12.6 pH. Let me see. Two significant figures here. So we need that. 2 decimal places. Okay, that one's easy. This one's a little harder. All right. The pH of a solution is 5.85. What's the hydrogen ion concentration of this solution? Right, we know that one. If the pH is 5.85, then the hydrogen ion concentration is going to be 10 to the minus 5.85. Right. Following the same procedure I showed you earlier. And there it is, step by step. Well, almost. So you say, now why is this negative? Because negative log, that negative has to be transferred over to the 5.85 before you can do the anti-log.
Where's the 1.4 come from?
10 to the minus 5.85. 2 decimals, 2 significant figures, that's right. 1.4 times 10 to the minus 6.
Oh, okay.
Yeah. So that would be the anti-log of 5.85, the negative 5.85. All right. So we're gonna get to the easy way to solve that problem. 0.040 molar is that short-term memory loss? Yeah, 0.04 molar hydroxyl. We wanted to calculate pH. Okay, we're going to show you the quicker way. All right. So this is true. That's our equilibrium expression for the autoionization of water. If we take, and we can do this, right? Mathematical, it's just simple math. Take the negative log of that entire equation, right? I probably should do this now. So it's Kw equals hydrogen ions times hydroxyl ions. Right? Take the negative log of the entire thing. Right? So the negative log of this would be the negative log of Kw. Negative log of hydrogen ions would be, well, if we take the log of this and time, the log of hydrogen ion times hydroxyl is the same as the log of hydrogen ions plus the log of hydroxyls. That's one of the log rules. Okay, but this is negative, so we got a negative log of hydrogen ions plus the negative log of hydroxyls. Okay, if we use Sorensen's naming convention, they would just stick a small p in front of each one. Right? So this one would be P Kw. Okay. This one would be pH. We already did that one. This one would be POH. Okay. All right. So far, so good. Now, if we put values in here, we know that this one, neutrality is our example. This one is 10 to the minus 7. This one's 10 to the minus 7. This one is 10 to the minus 14. Right? So the negative log of 10 minus 14 is 14, isn't it? And in this case, if we put in 10 to the minus 7 here and 10 to the minus 7 here, it'd be 7 plus 7. But it doesn't have to be, right? It could be 6 here and 8 here. Or it could be 3 here and 11 here. As long as it's 10 to the minus 7, 10 to the minus 3 and 10 to the minus 11. Then you take the negative log of each one of those, and this could be 6, 8, it could be 5, 9, it could be 4, 10, it could be 3, 11. Right? As long as they're both equal to 14. Okay, so if we want to, and this is always equal to 14, right, at 25 degrees. So this expression is equal to 14. So before, all we had to do was find the POH, take the negative log of 0.040 molar, and then subtract it from 14, we got pH. There you go. Okay, so if we do it that way, of course, this one's still going to be, well, POH there, we had what? 4. pH would be 4, so POH would be 14 minus 4, 10. 10.00. And this one, the POH would be what? 0.04. That's 0.04, take the negative log, and that's 13.979 or 13.98. Is the POH. Oops, excuse me. What did I do wrong? Oh, I misread my, 1.40. Excuse me. This is equal to the negative log of 0.040. So if we subtract that from 14, that's 6 and 12. 12.6 pH. Okay,
It's a lot easier to get the PLH.
and subtract it from 14. Yeah, oh yeah.
A lot easier to get that.
Yeah. All right, how we doing? 15 minutes. pH of a solution is 5.85. What's the OH minus for this solution? Well, 14 minus 5.85 is what? That's 5, that's 1, and that's 8. So this is the POH. And then the hydroxyl ion concentration is 10 to the minus 8.15. .08 times 10 to the minus 9. Let's see. Should be 7.1 then. Okay. Hard to see. There you go. Okay. We're eventually going to solve acid-base problems in terms of equilibrium. So we're going to see the ice table again. But before you can build the ice table, before you need to know what is the controlling reaction. Right? So that's why we say, what are the major species in solution? When you first start the experiment, not after it's finished, but when you first start it, what are the major species? And then you determine from that, what are the possible reactions that could occur? And you throw out the ones that make no sense or that are not dominant, and you keep the one that's dominant. And then you ask yourself, is this reaction better solved in terms of stoichiometry first? Let it go all the way to completion. And then when you get those products, you set up another reaction, which is in equilibrium. Sometimes that's more effective, and that's a quicker way to solve it. Sometimes that's the only way to solve a problem, is to let it go to completion and then work your way back as an equilibrium. And then if the question is, what's the pH, then you extract the hydrogen ion concentration from your ice table and calculate the pH. Right, we're going to have several examples, of course. So here, in the next couple of slides, all we're going to do is just say, what are the major species? So we have an aqueous solution of 2 times 10 to the minus third hydrogen chloride in aqueous solution. What are the major species? Okay. Well, HCl is a strong acid. So it dissociates into hydrogen ions and chloride ions. When you put it in solution, there's no time lag. It just goes hydrogen ion, chloride ions, and there's water left. So those are the major species. So what's the pH? Well, since this completely dissociates, right, there's really no equilibrium here. So this concentration is going to be the same as that one because it's 1 to 1. All right, so we can calculate the pH as negative log of 2 times 10 to the minus 3 molar. Okay. And that should be 2.70. Strong acids are like that. If you know the concentration of the acid going into solution, you can calculate the hydrogen ion concentration. Unless there's one exception though. If you're trying to create a solution with a strong acid that has a lower concentration than the water produces, then it's a wash. I mean, there's no pun intended, but it has no effect on the pH. Right? If you have neutral water, which is 10 to the minus 7, right? 10 to the minus 7 molar in hydrogen ions. And you put this strong acid in here at a concentration of 10 to the minus 9 molar. What effect is that going to have on the pH? Nothing. It's still neutral. Because it's 2 orders of magnitude too weak. In fact, I may have one of those in here. Yeah, I think this one is it. 1.5 times 10 to the minus 11 molar HCl does what to the pH? Well, wait a minute, it says 10.8. What did I do wrong? Oh. All right. This is true. But if we know that the molar concentration of hydrogen ions is 1.5 times 10 to the minus 11, how did it get there? Right, that takes into account water also. It got there because this pH is, we just calculate the pH of that. And that's 10.8, which means the POH, this is basic solution. So the POH then would be 3.2. All right, when we add nitric acid is a strong acid, so it's completely to the right, produces hydroniums and nitrate ion. So why is this reaction not likely? Right? If we put this one in aqueous solution, it's going to dissociate like that and like that. Shorthand version. Right? This is a strong acid. This is a very weak base. Very weak. So when you put, if you were to put nitrate in solution by itself, is that a valid reaction? No. Because this is such a weak base, it's not going to take a proton from water. It's essentially all this way. That reaction will not go. And let's see. Why is the reaction not likely? And then we get our explanation. Well, the reaction that controls the pH at this point is the autoionization of water. In this case, water is not a major contributor of hydrogen ions. Did it give us? It didn't give us a concentration. All right. So if we calculate the pH of nitric acid at this concentration, and we see that the major species are hydrogen ions, nitrate ions, water, and there's no HNO3 left. It's gone. So all we have to do is take the hydrogen, is the nitric acid concentration, which is much, much higher than water. Water is going to be 10 to the minus 7 molar hydrogen ions at the beginning. And well, 1.5. This is the molar concentration added. That's 5 orders of magnitude stronger, right? So you'd have to go out to 6 decimal places to see any influence of that on it. So we just calculate the pH based upon this value. It's 1.82. Okay, so this just gives you step-by-step list the major species in the solution, choose the species that can produce hydrogen ions, and write balanced equations for the reactions producing hydrogen ions. And this is for weak acid problems. You would follow a similar procedure for weak bases. Using the values of the equilibrium constants for the reactions that you've written, decide which one is dominant and write the equilibrium expression for the dominant. And then, what are the initial concentrations of the species? Then you set up your ice table and you want to pick your unknown. If it's asking for pH, then you want your X, your unknown, to be hydrogen ions. So it's simple calculation from that point, if at all possible. Okay. And then you'll have to always keep in mind the 5% rule, right? We covered that in equilibrium, didn't we? 5%. If you find that it's convenient to throw out one of your unknowns in your setup equilibrium because you don't want to solve a quadratic, then you have to calculate the value that you would get for the X under those circumstances. And then you would put that value back into the expression and see, is it within 5% of the K value? You put that value back into your equilibrium expression and calculate it. And that value that you're saying is K based on your X, compare it to the K of reality. And is it within 5%? We'll have some examples to work on. We were at the point where we were introducing concepts that we need for solving weak acid equilibrium problems. And the first thing you do is actually heard something. What I would do first, well, no, that's a good way to start. What are the major species? And what we're talking about now is if you put something in solution, what does it do before any reactions occur? So it's not really at the very beginning where say the salt you're going to add is over here and the liquid's over here. Now we want to put the salt in the liquid and see what happens to that. That produces the major species. So in this case, we have a solution of weak acid. And if we have a weak acid, which is hydrogen cyanide, and then when you put it in solution, of course, it's what? Starts with a hydrocyanic acid. So if this goes into solution, then it's going to, so I guess what I'm doing is, I'm going ahead and draw this one. And these are aqueous, this is aqueous. This is a weak acid with a Ka of 6.2 times 10 to the minus 10. What are the major species here that are in that solution? Well, there's one, there's one. Right. Hydrogen cyanide and water. Those are the major species. Now, I'm not sure if we're going to, how far we're going to go with this, except to say that these are not major species because this is a weak acid. Right? This expression here would be written how? Right? And this is the shortened version. Right? We didn't put water in here as a reactant, which it should be, but the math doesn't require it. So if we write this as an equilibrium expression, it'll be equal to this, the same as if we put water in there. And this one, divide by this one. So that means that if this is a very, very, very small number, these are insignificant. They're just really tiny amounts, and this is most of them. That's why we say this is the major species along with water. Okay. All right. So, okay, so the slide writes the whole thing out the way it should be. Makes water a reactant. And if we put water in here, that makes this a hydronium ion. But still, the concentration of this and the concentration of hydronium are exactly the same. And the water is not placed in the equilibrium expression because it's a pure liquid. They don't count. Pure liquids and solids don't count. Okay, so we have these two reactions to deal with. This one at 10 to the minus 10. And then what's water going to do? Well, water, I'm going to write it simplified. Water dissociates, or actually ionizes, into these two. Right? And here. Okay. I was about to write water aqueous. What other kind is there? So what's the KW for water? 1 times 10 to the minus 14. So which one controls the pH? Which one is the most dominant? This one. Here. Because look how small that is compared to this one. That's 4 orders, this 6.2. So it's about 3.5 orders of magnitude difference between the two. That means that water will have no measurable impact on the pH of this solution. So that means we proceed with the equilibrium with that equation. Okay. All right, so it looks like we're done with that. We're going to another one. This one, I believe, we're actually going to try to solve an equilibrium with a weak acid. And hydrochloric acid is weak. Hydrochloric acid is strong, actually strong, stronger, stronger, keeps getting stronger as you go down. HF is weak. You remember one of the problems that we studied had that as a sequence. Which one was stronger? Right. HF is weak because even though its electronegativity is high, it's the highest in the table. The strength of the acid is determined by how easily you can remove that proton. And fluorine is a very small ion, or small atom actually, because it's a covalent bond between hydrogen and fluorine. They get so close together, and the strength of the bond is determined by several factors, one of which is how close are the two atoms. Right? Hydrogen and fluorine are very close together. So even though you've got the strong electronegativity, which would draw electron density away from, right, like that, it would draw electron density away from hydrogen and start making it slightly positive. The two are so close together that the strength of attraction is strong enough to impede the hydrogen leaving that molecule. So HF is a weak acid. All right, back to the problem. We want to calculate the pH of an aqueous solution of HF. So we got HF here, aqueous solution. What does it do? What does that molecule do in water? Well, to a limited extent, it ionizes into these two. And the Ka of that one is equal to 7.2 times 10 to the minus 4. So is it weaker or stronger than hydrocyanic acid? It's stronger. That's a bigger number than 10 to the minus 10, right? That's 6 orders of magnitude stronger. But it's still weak. So, the pH of a 0.5 molar aqueous solution. So we're starting with, and we can make the same argument here. What are the major species? That one and water. And compare the two. Water is still 10 to the minus 14, which means now it's 10 orders of magnitude stronger. Right? So this one controls the pH. And we start off with a concentration of 0.05 or 0.5 molar. That's the initial concentration. Right? So we're going back to our equilibrium ice table. Before it dissociates, this is 0 and that's 0. Okay, so we're able to determine based on that information which way the reaction is going to go. That way. Right, so it's going to produce, and since we're looking for pH, we want to make our unknown that we solve for equal to this value. So that if once we solve for that x, all we have to do is take the negative log of it, we've got our answer. So we're going to add x over here, and we're going to add x here, and we're going to subtract x here because it's 1 to 1 to 1. And this is characteristic of acid-base acid dissociations. Since they only occur one proton at a time, if you've got a molecule with more than one acidic proton, the reactions occur one at a time. So it's always just 1x. Okay, so now at equilibrium, what do we have? We have 0.50 minus x. We have x, and we have x here. Okay. So what do we do with that information? Solve this equation, right? Okay, so 7.2 times 10 to the minus 4 is equal to that one divided by this one. Okay, and we just fill in the values. This is an x, that's an x, and this is a 0.5 minus x. And it's still equal to that number. Okay, if we're going to solve for x, we've got to get all the x's on the same side. But you can probably see that what we're facing is quadratic. I mean, these two are going to be a squared x. This one's going to be a single x. And then your ABC, C value. Right, so we're going to use the trick I mentioned earlier. Since this is such a small number, that x is going to be very small compared to this value, 0.5. It's going to be extremely small. So what we can do is get rid of this x. We can say it's approximately equal to, I'm going to go ahead and square that one, divided by 0.50. And that's also equal to that value. Now we've gotten rid of the quadratic. And if we take 0.5 and multiply it by that value, then that's equal to x squared. Right? So what's half of 7.2? 3.6. 0.5 times that value is 3.6 times 10 to the minus 4. And then x would be the square root of that value. If I can do that one in my head. I know you're disappointed, but price is getting on me. Okay. Now take square root of it. So I get two significant figures. 1.9 times 10 to the minus 2 is equal to the hydrogen ion concentration. Now we have done a 5% test on our equilibrium before, correct? Then I show you a 5% test. What you do is you take that x and you plug it into the true value. This value goes in there, there, and there. And you calculate what that is and compare it to the true K. Is it within 5%? And to save us time, I'll just tell you it is. It is within 5%. So we were justified in doing this. Okay, so if that's the hydrogen ion concentration, what's the pH? Negative log, correct? Of 1.9 times 10 to the minus 2. So I just take the log of this and change the sign. 1.72, let's see. Two significant figures, that means I need two decimal places. Yeah, I'm just checking my exponents, 1.72. pH. Now let's see if I got it right. Okay, major species, did that. Compare the two, we find that HF ionization is controlling reaction. Okay. And we set up our ice table, and that looks familiar. We're saying that these are approximately 0 because actually that one is 0, but this one is approximately 0 because water has dissociated into a small amount, but it's not controllable. So we're going to call these 0. Plus x, minus x. We'll get those values. And there's our Ka. Let's see, how far did I go with this? Okay. Yep. Fill in the values. Okay. Assume X is too small for 0.5. And then solve for X here, and then solve pH. Okay. So either I'm right or we're both wrong. Right. I think we're right. Okay. Oh, we actually did the 5% here. Okay. So you'll notice, let's see. Here's where we substitute the X's right across here. There's an X, there's an X, and there's an X. Then we calculate 7.8481 times 10 to the minus 4 and compare that to 7.2. And here's the comparison. It's kind of like doing a percent error, right? There's the calculated value, and these are the accepted values, and it turns out it's 3.9%. Within 3.9% of the expected value. Pushing the wrong button. So why is it working? Okay, next concept. Remember when we were first talking about equilibrium, and we drew a distinction between the equilibrium constant and the equilibrium position. The equilibrium constant is a constant at a given temperature. The equilibrium position changes depending on how much you start with. But you still, once you incorporate the equilibrium values from that new concentration, you get the same constant. Well, similar to that is this concept of percent dissociation. When we measure the dissociation of an acid, we compare the amount that was dissociated with the initial concentration. So we could take the amount of HF that was dissociated, which would be X, and divide it by the 0.5 and times 100, and that gives us a percent dissociation of that acid. Right? This value changes depending on two factors: the Ka for the acid and its initial concentration. As it turns out, the lower the initial concentration, the higher the percent dissociation. And I'm going to talk a little bit more about that and try to explain it. But it seems counterintuitive, right? You would think that, well, if I got more acid there, then it should be more dissociated. Well, the way we calculate it, that's not necessarily true, right? Because it's ratio to the initial concentration, you get more dissociation relative to the initial concentration if the concentration starts lower. Okay, that's the whole concept of behind percent dissociation. Let's see. What are we doing here? 8 molar formic. Let me check my hard copies. Might have some slides out of order. Oh, okay. Okay. We are building on that concept. So if we've got 8 molar formic acid. So what's formic acid? Well, it's a carboxylic acid, right? So it's going to start off like this, like that, and like that. Okay. There's your acidic proton. And then anything else out here determines what type of carboxylic acid it is. And with formic acid, that's a hydrogen. Okay. Formic acid is named after the genus, maybe it's the family of ants. Because when they bite you, especially fire ants, when they bite you, they inject formic acid into that wound, and it burns like nobody's business. Well, the Latin, I think the Latin genus for ants is forma. So we just named the acid after the ants. Okay, that's formic acid. If we wrote it in standard form, we'd have one carbon. We'd have, let's see, I think the hydrogen's coming next, and then the oxygen. So that's formic acid. Oh, excuse me. My mistake. There are two oxygens and two hydrogens. And we always write the acidic hydrogen first. Okay. So now that I got it right. Okay, and this is going to dissociate or ionize into a proton plus the formate ion. That, okay, we're starting off with 8 molar, right? Nothing here, nothing here. And the K is the question. They want to know what the K is. Right? The K would be expressed this way. O minus and formic acid on the bottom. Like that. So what we need is values for the equilibrium concentrations in order to solve this. So the trick here is to know what's the change. The information we're given is 0.47% ionized. So 0.47% of that becomes that. So we're going to add 0.47%. Well, percent is a dimensionless number, right? And it's parts per 100, right? And that's not 100. So the best way to solve this one is to convert percent into a decimal fraction. So what's 0.47% is the same. Before you multiply it by 100, what is it? Right, it's 0.2, 0.0047. Right. I think that's right. 1, 2. Yeah, that's right. So we would multiply that times 0.0047 or 8 times 0.0047, and the same thing over here. So how much is lost over here? Well, same amount. Right. And at equilibrium, the calculation's already been done. At equilibrium, we have 7.69624. And here we have 3.76 times 10 to the minus 2. Molar. So we plug those values in here. And let's see. There we go. Plug those values in, and we get 1.78 times 10 to the minus 4 is the Ka for that acid. And all we had to go on was the initial concentration and the percent dissociation. All right. Oh, pH. Well, this was what? Bring me back up. 1.78 times 10 to the minus 4. So we don't have to spend a lot of time throwing the major species up there and comparing them to water. We know that that's stronger than water. So we already have the hydrogen ion concentration right here. All we need to do is take the negative log of it. And that gives us a pH of 1.42. Okay. All right. So let me leave that up there since we're still talking about formic acid. If the concentration of formic acid is 4 molar instead of 8, right? We have 4 molar here instead of 8. What would the percent dissociation be? Higher than, lower than, the same as? But it's not the same as. It would change. But with a lower concentration, the percent dissociation should be higher. Based on what I told you. Excuse me, I answered the wrong question. What's the value of K? You wouldn't let me get away with that. K is the same, no matter what we do. Right? Well, not no matter. If we change the temperature, the K changes. But as long as they're the same temperature, it doesn't matter what the starting concentration is. The K is going to be the same. I hope the next slide is percent dissociation. Yeah. Percent ionization would be higher. Okay. I'm getting ahead of myself. So I think this is going to be an explanation, I hope. Yes, this is an explanation of a justification, I should say, for the rule that I just gave you, that the lower initial concentration of the acid produces a higher percent dissociation, or percent ionization. Okay, consider this generic acid HA with initial concentration of HA sub-zero. That little zero means initial concentration. Okay, so there would be our dissociation equation. And there would be our Ka expression for that acid. And if we write out the concentration at equilibrium, then we would have to subtract some of this dissociated X from it. But X is so small, right? We're going to say the concentration of acid doesn't change from its initial concentration. Very, very little. Okay. So what we're saying is that we're subtracting that X, and this is drawn from that ice table. Right? It's that same X in the same position as always. That the concentration of hydrogen ions and conjugate base are equal to X. Right? We're going to keep those. Okay. So there would be our expression for the initial condition. Right? With that assumption that the X is too small, so we throw it out. Okay. So what happens if we added enough water so that the initial concentration of HA now is 1/10 of what it was? Right? So we've only got, say we had 100 mils of solution and we took 10 mils out of it and re-diluted it to 100 mils. That would be a 1/10 dilution. Okay. All right, we've diluted it. That means the initial concentration is 1/10 of what it was. And so we're going to go back and we're going to substitute those values in there. The new A minus and the hydrogen ion concentration now is X divided by 10 in our table. Maybe I should have drawn the table up there. Should I do that? Okay, I'm going to have this, initial change, equilibrium. Okay, initially we've got this one and 0 and 0, and this change is going to be plus X. That, then we have X here, X here. This is going to be minus X, and this would be, at equilibrium would be this one minus X. We're saying that's approximately the initial concentration, which is HA. So we're saying that this one is essentially that value. Now for the next one, we're going to say that we're diluting it by 10. Right, so we're going to take 1/10 of that, which means 1/10 of that, which means 1/10 of that, 10, and this is going to be a 10, and these are going to be a 10. Okay. All right. So here's the new equilibrium concentration, which is this one divided by 10. Okay. So far, so good. Now that we have stressed the system by adding water and reducing the concentration of the products, which way will the reaction proceed? We've reduced the concentration of this one. This one didn't change, but almost nothing, right? So we're saying it's basically, well, it did change by this factor, but if we dilute the whole thing, which way does Le Chatelier say it's going to go? It's going to move to the right. We've decreased the concentration of the products, so the solution should migrate to the right. And if we calculate the Q for this new, that one times that one divided by this one, then we find out that the Q is 1/10 of the K value. Okay, so if the Q is 1/10 of the K value, which way is it going to go? If the Q is smaller than K, Q is smaller than K, that means which part is smaller? The product side is smaller. If the product side is smaller, that means it's going to shift to the right. Okay. So if it shifts to the right, that means this value is increased and the percent dissociation, the percent ionization goes up also. So that's the explanation for why it's counterintuitive. Decrease the concentration, initial concentration, increase the percent ionization. Okay. The pH of 4 molar formic acid solution should be compared to the pH of the 8 molar. All right. Now here's where you can get twisted around. When we have more of this initially, say we have 8 rather than 4. Let's go the other direction. We have a pH, what was it, 1.42? Yeah, 1.42 pH, and that was with 8 molar. Yeah. Right? So that's simply the negative log of the hydrogen ion concentration. Well, the percent dissociation is a ratio. It's a ratio of this one to that, to the initial concentration. Right? But if this is lower, then the actual amount of this is going to be less, right, by a factor of 10, right? So the pH of this concentration should be less, excuse me, not less than, greater than 1.42. It should be more basic. Okay, there's another twist. pH should be higher. Yes, the equilibrium does shift to the right, but it shifts to the right based on a lower initial concentration, which means the hydrogen ion is, the concentration is lower than the 8 molar. All right, so what would it actually be? Well, if we run through this entire calculation again, we find that the concentration, the molar concentration of hydrogen ions is 2.665 times 10 to the minus 2, and the pH is, oh, it wanted dissociation, correct? Oh, percent ionization. Yeah, okay, so this is the X value, and we ratio that to 4. Let's go to the next one. There it is. Okay, so we're ratioing the determined hydrogen ion concentration to the initial concentration. And yes, it does. It picks up. 0.67. Versus what? What was it before? We actually told. 47. 0.67 versus 0.47.
Next slide, you can get the age.
Okay. This one's 0.67%, and this one is 0.47%. Okay. In the next slide, we calculate the pH. Based upon that hydrogen ion concentration, 1.57. So it's 1.5. So the pH does increase. All right. Bases. Bases are a little bit, well, it depends on who you talk to. If you talk to Arrhenius, you have to have a hydroxyl in the molecule. If you talk to Lowry and Bronsted, you don't need, you're really based upon the movement of the hydrogen ion. But a basic solution is one where the pH is greater than 7, because 7 is pure water, neutral. Now you can have pH 7 in mixtures. You can create a solution that has a pH 7. In fact, sodium chloride solution will be pH 7. I'll talk about that a little in a minute. The strong bases, right? And the concept here is similar to strong acids. The amount of dissociation. Strong base virtually completely dissociates in water. Lithium, sodium, potassium, they're all alkaline metals. Those hydroxides are strong bases. Calcium hydroxide is a strong base. Magnesium hydroxide is not. But calcium hydroxide is a strong base. The problem in understanding that is calcium hydroxide is only sparingly soluble in water. But by our definition, whatever goes into water, whatever dissolves in the water, completely dissociates. So it's a strong base. Okay. So there's a twist of words there. All right, and the pH would be 14 minus POH. That hadn't changed. All right. What's the pH of a 1 times 10 to the minus third molar solution of sodium hydroxide? Well, we know it's a strong base, so we just calculate the POH, that negative log of 1 times 10 to the minus 3 molar equals what? Well, that's POH would be 3, right? 1, 2. That would be the pH. Oops, sorry. That's POH. And the pH then would be 14 minus that. Okay. There we go. All right, what's the pH of that solution? I thought we just did that one. The pH of a 10 to the minus third molar sodium hydroxide. Oh, calcium hydroxide, excuse me. Yeah, read my own problems. So what would be, if you actually got that much 10 to the minus third molar calcium hydroxide to go into solution, right? 1.0 times 10 to the minus 3 calcium hydroxide. How much hydroxide do you have in there? You have twice as much. So the hydroxide concentration is 2 times 10 to the minus third molar hydroxide. So the POH would be the negative log of that value, which is, let's see, two significant figures equals 2.70 POH, and then pH would be 14 minus 2.70, which would be 11.3. Let's see, that's got to for 0 pH. Okay. That can trip you up if you're not paying attention to the hydroxyls and the hydrogens that are produced in the reaction. Did I skip a slide? No, I didn't. Equilibrium expression for the conjugate base uses Kb. Okay, so we're looking at this cyanide ion in solution. So how did it get in solution? What do you think? Any ideas? How would you put cyanide in solution without the acid part so that you could get this reaction? You need a soluble form, right? A soluble form of cyanide ion with a cation that does not react with anything in your solution. So sodium cyanide would be a good choice. Probably the cheapest. That way you get cyanide ion plus water. And this reaction, hydrogen cyanide is a weak acid, correct? So this is the conjugate base of weak acid, which makes it what? A very strong base, which means it's hunting for protons. So it's going to take a proton from that water and make the acid and leave you with hydroxyls. Okay. So the Kb expression is right there. HCN times OH minus divided by Cn minus. This doesn't count because it's pure liquid. And that's your Kb expression. Right. So did I get my slides jumbled up? It just didn't seem to flow. How would you calculate the Kb here for this one? Well, if you knew the values, right, you could do that expression. But if you didn't, you need 10 Kb, right? 10 to the minus 14 divided by Ka. And we determined that last Tuesday, correct? Because Ka times Kb equals 1 times 10 to the minus 14. Right, so we can calculate the Kb for that one, since we already know the Ka for hydrocyanic acid. All right. That's old stuff. We've done that already. What's the pH of a 2 molar solution of ammonia, where the Kb is 1.8 times 10 to the minus 5? And there's the reaction that Kb is associated with. You put ammonia in water, it reacts with water, and there's your Kb. So what's the pH of this one? Do I have this one worked out already? Yeah. Except I didn't create an ice table, so let's do that. Do I have time? Probably not. Okay. Water produces ammonium polyatomic ion plus hydroxyl polyatomic ion. All right, so what's the initial concentration? 2 molar, right? 2 molar of this. That doesn't count because it's pure liquid. And we're saying that we're starting off here and here. I mean, the Kb is 10 to the minus 5. Is it going to have any competition from the association of water? No, because water is 10 to the minus 14. Okay, so what's the change? Well, we're going to take some of this and we're going to put it over here. Right? Well, that means at equilibrium, we have 2.0 minus x and x here and x here. And that would be our expression. All right. KB is equal to 1.8 times 10 to the minus 5 is equal to x times x, which is x squared. And we're going to assume this is so small because it's 1.8 times 10 to the minus 5. This is approximately 2.0. And then solve for x. And x is hydroxyl concentration. Okay. So there's our hydroxyl concentration, 6 times 10 to the minus 3. And if your K value is 10 to the minus 5, you can assume that you're within the 5% to do this, especially if this is greater than 1. Okay, there's the POH and there's the pH. Okay. Stop me if you have questions. Okay, I mentioned the way that acids dissociate one proton at a time. This only happens for diprotic, triprotic, or those fall into a category overall called polyprotic acids. So what are some possible examples of polyprotic acids? About H2SO4. Sulfuric acid, right? That's got 2 protons. How about this one? Phosphoric acid, right? This one would dissociate 2 protons. This one would dissociate 3, but they always occur one at a time. There's an equilibrium set up here between these 2 and that one. So what would its conjugate base be? SO4 minus. Okay. And then this could dissociate. It'll be a completely separate equation. Another proton. Now you have SO4 2 minus. And this would have its own Ka. This would also have its own Ka. You could do the same thing with this one. H2PO4 minus. And then that one could undergo its own equilibrium, dissociating another proton, PO4 2 minus. And then that one would dissociate the last one. PO4 3 minus. Okay, each one of these would have its own K. One of the main points of this slide is, as these acids dissociate one proton at a time, this K is a certain value. The second K is going to be a much smaller value. And if you need some way to rationalize it, what's happening here? Well, we're removing a proton from a neutral body, right? So it takes a certain amount of energy to get that proton loose. And that contributes to the Ka1. But by this time, you've got a negative ion. Try to remove a positive charge from a negative ion. It's a lot harder. That makes this one a smaller value. You don't have quite as much over here by comparison as you did up here. So this is always smaller than that. Okay. And by the same logic, this one would be smaller than the first one, and this one would be smaller than the second one, which was also smaller than the first one. Okay. And that's true with any acid, polyprotic acid dissociation. Now, I don't know if you're wondering this, but the thought just occurred to me. How does this affect bases? If you have a dihydroxyl base like calcium hydroxide, how is it affected? Well, as it turns out, there's a difference between the way they produce their ions. These are covalent bonded hydrogens. That's why we call it an ionization. We actually have to form the ion. But the bases with hydroxyl in them, those are ionic compounds. All right, so all you have to do is get those ions apart. That's why we call that a dissociation. We call this an ionization. And we're mixing our terms up here. When we say dissociation there, it should be ionization. It's ionization. Okay, let's move on. So here are the actual values for these Ka1, 2, and 3. Right? And there you see that we go from the first dissociation of phosphoric acid, 10 to the minus 3, 10 to the minus 8 is 5 orders of magnitude difference. And then the third one is another 5 orders of magnitude. So it becomes more and more difficult to remove that proton. That doesn't mean it can't be done, right? If we use a strong base, sure, we can strip every proton off of that. And that's what you do in a titration. But we're not going to titrate polyprotics today. We're going to titrate a monoprotic acetic acid. So it's a simple curve. Okay. This titration curve, as we add base, you get 3 stair steps, 1 for each hydrogen. Okay, so there's Ka1. Oh, this is actually a problem. 1 molar solution of H3PO4. And we're looking for the pH. Okay, so these equations are derived from that ice table, and all these ice tables look alike. Right? They have the x's on this side and minus x on that side. They're all the same. So that's why we didn't put them all up here. But if we write it with the hydrogen ion and the conjugate base in the numerator and the acid or the molecule that's on the left-hand side before dissociation, then the expression looks like this all the time. And x is, again, considered to be so small that we actually have that expression and we just solve x. And that's 0.0866 hydrogen ion concentration. But maybe we better check the 5% rule. Right? We might have missed it on this one. So let's see, if we put in that value in our expression, say, okay, the K we're expecting is 8.2 times 10 minus 3. What's the K we actually get? 7.5. Whoa, we're way off. Okay, so we missed it. We missed it. So what do you do now? Well, you have 2 choices. You can either go back to the quadratic, or you can do a successive approximation. Right? So what we would do then is we would take this value for x here, have a for x, and go back and substitute that value instead of dropping it. Where is it? There it is. Instead of dropping that x, we substitute that first determination of x in that position. Not for these 2, just for that one. And then solve it again. And we get a different x. Actually, a closer approximation to the value that we would get if we did quadratic. And then we test the 5% again. And usually for our problems, 1 iteration is all it takes. And it gets you under 5%. Some chemistry problems that are much more complex than this, successive approximations is the only way you can solve them. Right? They're too complex. They'll have not just quadratic, they might have, what's the next one? Cubic equation. Have to solve, there is a formula for cubic solutions. But once you get to the 4th, 5th, 6th, 7th polynomial powers, I mean, it's a losing battle. Successive approximation is the only way to do those efficiently. And if you have a computer program to do it for you, then snap your fingers and it's done. Okay. So that one failed. Successive approximation then substitutes that value for x in the denominator, and we recalculate the x. Now the new x comes up as 8.278 times 10 minus 2. And then we substitute that one in our calculate Q for that one. And does it come close to the K? Well, yeah, it's under 1% now. Okay. So that method will solve the problem for you without having to do quadratics. Okay. So calculate the pH of this solution. All right. Now that we have a value that's under 5%, then we can calculate the pH as 1.08. Now that's the pH if we assume only one proton dissociation. The question is, will the second proton dissociation affect the pH? And the shorter answer is no, because it's 5 orders of magnitude away. I think, wasn't it 5 orders? So it's like controlling those or comparing those major species, right? The second and third reactions have no effect on the pH. And I may have the slides may go through that. Let me see. Yeah, I think they do. All right, so that's for the pH if we consider only the first dissociation. Now, what if we, okay, this problem says, all right, we're interested in the phosphate concentration at the very end. All right, so it's got to go through these successive ones to get down to here. All right, so you're going to produce a little bit of this, and then the little bit here is going to make even less here, and this is going to produce even less there. So you would have to go through each successive calculation in order to find out. Right. So that one takes our first solution at 1 molar, and it puts the values that we have in there. That these are the starting values for the new. Right. So the starting value here is from here, 8.28 times 10 to the minus 2. So it'd be over here. And then this would be the same value, and this would be 0. And then you go through the ICE expression. And since we know the K value for the second dissociation, second ionization, excuse me, we can calculate the second one. Right? And there's X for the second one, which is essentially X for the first one. See what we've done there? When you put everything in there as X, and we say that X is so small for this part, right? Where is my arrow? It's in there. There it is right there. That X is so small, we're going to say that it's gone. That means that this one cancels that one, and that's X equals X. Right? So we didn't get any change in the X value. But that doesn't help us solve. That doesn't help us solve the final expression, right? We're looking for phosphate concentration. So for the let's see. Oh, we're still doing that one. Okay. So what's the hydrogen ion concentration here? Oh, it was. Excuse me. All right. I hope I'm not confusing everybody. There we go. The Ka. The second Ka is 6.2 times 10 to the minus 8. So since we've canceled those two numbers over on the right-hand side, X equals the K. So that's our new starting point for X on the second determinant, on the last determination. Okay, so we got that one. Let's see. Hydrogen ions are approximately the same. We needed to determine what the hydrogen ion concentration was, and it hadn't changed from here to here. Right? But the dihydrogen phosphate ion did change. So notice that what we've done here is we put the new, excuse me, there it is, there's an arrow. We put the new value for the hydrogen phosphate is actually equal to the hydrogen ion concentration. And this one is the concentration of hydrogen ions. And this is our unknown. Now, if we solve for the phosphate ion, we should get the answer we're looking for. So it is extremely small value. Step by step. That's where I would have paused if we had made it that far. So let's look at salts. Right? What is a salt? The chemical definition of a salt is actually one of the products of an acid-base reaction. So our example here is sodium hydroxide and hydrochloric acid. Those are Arrhenius acid base. When you react those together, what do you get? Well, the sodium, it's like a double replacement reaction, right? Where the cation goes with the anion of the other molecule and vice versa. So we swap sodium with hydrogen, and that's sodium chloride. Okay, so that's one of the products. In fact, that's the definition of a salt. And then what do you got left over? Well, you got a hydrogen ion from the acid, and you got a hydroxyl from the base, and that gets together and produces what? Water. Okay. So this is the typical reaction for any acid base. An acid plus a base yields a salt plus water. And we're having to confine ourselves for the moment to Arrhenius type bases. Okay. So what would the pH be for a strong acid, strong base solution? It's neutral. It's neutral because they are completely dissociated. And what do you have left over? Let's take potassium chloride, KOH plus, excuse me. No, that's right. KOH plus HCl. Right. This would produce potassium chloride plus water. Right. Remember when we wrote the complete ionic equations and the net ionic equations? Yeah, okay. So this would, in solution, this would produce that ion, that ion, that ion, and that ion. And they're all aqueous. Right? And this is also in solution. With chloride ions, right? How do you know? Because potassium chloride is completely soluble, right? No matter how you make it. If you put it in there as light salt, right? It's still the same thing. And then you have water. Okay, that's the complete ionic equation. What's the net ionic equation? Right there, that one's gone. This one, that one's gone. The net ionic equation, let me write it this way, is the hydrogen ion plus the hydroxyl ion yields water. That's the net ionic equation for every acid-base reaction. So if these are strong acid, strong base, they're completely dissociated, right? There's no acid, no base left over. Right? So all you have left is this one. And what does this one give you? A neutral solution. So strong acids and strong bases reacting together always produce neutral solutions. That was the easy concept. Okay. if the anion of the salt is the conjugate base of a weak acid. All right, so let's see what we got there. Let's pick a weak acid. All right, there's a strong base. Let's pick a different one. Let's say, let's do the one that we're going to do today. That one. And what's our weak acid? Acetic acid, right? HC2H3O2. And this is an aqueous solution. It's an aqueous solution. Okay. So when these react, we get what? Sodium acetate, which is soluble, and water. So there you have base, acid, salt, water. All right. But what do we have here? Well, sodium is a spectator, right? It goes out. Hydrogen ion depends on how this dissociates, right? It's going to make some of this and some of that. A small amount of this. But once you're over here, all the way to this side, I probably shouldn't do that yet. Once you're all the way over here to have the salt and the water, then what is this going to do? Well, the water doesn't do anything. It dissociates a little bit. But this one produces what? Sodium ions and acetate ions. Right? Well, and you do have water. We should keep this one. All right. So this is the spectator. Right? So actually, we're looking at this ion and water. So what are they going to do? Well, this is a conjugate base of a weak acid, which makes it what? A strong base. That strong base is going to go looking for protons, and it's going to get them from water. So what we produce now is hydroxyls plus that. That's why when you put a strong base and a weak acid together, titrate them to where you've got equality here, the equivalence point where you used up these and make those, then the solution is going to be basic. Because this strong conjugate base removes a proton from water and produces a hydroxyl. And there's your basic solution. Okay? That's the chemical reason for weak acid, strong base makes a basic solution. The rule of thumb that is useful, right, is that if you put a strong base and a weak acid together, you get a basic solution. Okay, that's the rule of thumb. So by that token, what if you put, let's see, next one. What if you put a strong acid and a weak base together? You're going to get an acidic solution. Right? This is a weak base, so it produces a strong acid. By comparison. And there's the chloride. Okay, so we take this one and we react it with water, NH4 plus water, and that reaction produces hydrogen plus H3. And there's your acid. So this is the chemical reason, this is the rule of thumb, right? Strong acid, weak base makes an acidic solution. Strong base, weak acid makes a basic solution. And this is the chemical reason for that happening. Now, which one have we not covered? Weak acid, weak base. What happens when you put a weak acid and a weak base together? There's a tug of war. Right? And you have to actually know the values of their Kas and Kbs in order to determine which one wins. Okay, so you can't just looking at the problem without knowing what their K values are. You can't determine whether it's an acidic or a basic solution when you add a weak acid and a weak base together, unless they have identical K values. Right? If you have, well, it depends on the Ka and the Kb. Can't see my arrow. There it is. All right. If they have identical K, if the Ka for the acid is equal to in magnitude to the Kb for the base, then you will get a neutral solution. All right. Oops. That's there. Okay, I forgot I put this one in there. This is a qualitative prediction of the pH of a solution where you have acid-base comparison. The bottom one is where I say if the Ka of the acid and the Kb of the base are equal in magnitude, you have a neutral solution. If the Kb is a larger magnitude than the Ka of the acid, then you'll have a basic solution. And if the Ka is larger than the Kb, you'll have acidic solution. Okay. All right. I've only got an hour left. I hesitate to stall on this one. If we calculate the Kb values for these two, you know how to do that. Hopefully it's up here. Yeah, there we go. You just take the Kw and divide one, either the Ka or the Kb in it, depending on which one you want to solve for. In this case, the Kb for that anion would be 1.8 times 10 to the minus 5 divided into 10 to the minus 14. Now, this is your accepted value. I think it's either 1.8 times 10 to the minus 5 or 1.7. You have to look at the method and see which one is given. When you compare your results, okay, so we're going to use 1.8. 1.8 times 10 to the minus 5 is the Ka for acetic acid. That's your accepted value. So when you calculate the Ka for acetic acid using your titration data, that's the one you compare it to. Cyanide ion, 1.6 times 10 to the minus 5. Okay. So it's a stronger base than an HN is an acid. 10 to the minus 5 is much bigger than 10 to the minus 10. Okay. What we want to do here is to put these compounds in order of lowest to highest pH. And the first method is to use a qualitative approach. So, are there any compounds in this list that are composed of ions from strong acid, strong base interactions? Okay. Well, let's see. Are there any salts in there? Sodium chloride, strong base, strong acid, right? That's going to be neutral. So sodium chloride is going to be right in the middle. It's neutral, pH 7. Right? Lowest to highest. So this is going to be acidic side. This is going to be base side. So do we have any that are strong acids, right? That we can put way out here on this end? How about HBr? Right? Hydrobromic acid. That's very strong. Okay. How about, let's see, bases, sodium hydroxide. It's going to be way out here. Okay. Well, let's take one at a time. All right, so there's sodium chloride is neutral. Okay. Are there any strong or moderately strong bases? Yes. Sodium hydroxide. And ammonium is not as strong as sodium hydroxide, but it's in here somewhere. Come on. There we go. Are there any compounds composed of ions from weak acids and strong bases, which would be what solution? Basic, right? Weak acid, strong base. Weak acid, strong base. Yeah, sodium cyanide. Sodium cyanide is a strong base, weak acid interaction. Okay. All right. Are there any acids derived from halogens? Well, yeah, we got that one up here already, HBr. But HF is a weaker acid than this one. Let's see, what else do we have? We have to decide the relative position of hydrocyanic acid and ammonium chloride. Ammonium chloride is going to be an acidic solution. And HCN, so we have to say, all right, HCN is a weak acid, yeah. Is it a higher pH than either? Yeah, it's a higher pH than this one, it's over in here. While ammonium chloride is a salt of a weak base and a strong acid, this will likely push the pH closer to the basic than hydrocyanide. So we're going to say the salt, ammonium chloride, since it's compromised by its interaction with a weak base, is going to put it there, and HCN will be here, be more acidic than that. So I think, yeah, that's our reasoning based on, let's see, this is more acid than that one, than that one, than that one. That. Now, that's a qualitative approach. A quantitative approach will use the actual values. Let's see if I got them in the right order. Yep. This is a quantitative approach. And this just confirms by comparing the Kas and the Kbs, HBr doesn't have a Ka. It's too strong, right? Remember we talked about if the denominator is so small, it turns into infinity. Anything divided by 0 is infinity. The HF is the next largest Ka, and then ammonium chloride. I'm not sure why they put that Ka in there. Oh, there it is. Oh, HCN. There it is, 10 to the minus 10. And then I'm assuming this would have to be the K for that salt. You would have to actually determine the K for that salt. So we've got it listed as 5.6 10 to the minus 10. So we put it in the right position. This is a smaller value than that one. It makes it more basic. Then neutral. Then sodium cyanide, same thing. The Kb. Actually, in this case, the Kb is for the cyanide ion. That makes sense. So this one would be the Ka for the ammonium ion. All right. Okay, I understand that. Right. They're not actually reporting the K, they're reporting the Ka for ammonium ion. And this would be the Kb for the cyanide ion. And then a larger Kb for ammonia and then strong base. Okay, so that's the quantitative approach to order these by pH or acidity All right. If we got a 0.3 molar solution of sodium fluoride, all right, we've got a salt, strong base, weak acid. So it's going to, we know the solution is going to be basic, right? We know that right off the bat. The Ka for HF is 7.2 times 10 to the minus 4. What are the major species? When that goes into solution, what do you have? Well, you start off with sodium ions, fluoride ions, and water molecules, right? Right, those are the major species. That's the expression for the Ka for HF. But we don't have HF in there. We've got F minus as a major species. And sodium doesn't react with anything, does it? Well, we're going to propose. These are possible reactions. Right? The fluoride ion reacts with water, right? Makes HF and OH minus. That's a possibility. How about water and water? Yeah. That's self-ionization. How about sodium and water? Is it going to react? No. We're going to throw that one out, actually. Sodium and fluorine. No, that goes in, that's completely soluble. Right? So it's not going to go backwards. Right? So we can throw that one out. We can throw this one out. So really, we're just comparing these two equations, that one and that one. Right? So what's the Kb? Well, we got the Ka already. We divide that Ka into 10 to the minus 14, and the Kb for that reaction is 10 to the minus 11. Compare that to water, which is 10 to the minus 14. We know which one is dominant. Right? The Kb, the first one, is the dominant reaction because it's 3 orders of magnitude, 1,000 times stronger. Okay. All right. So now, after we did all that, we're going to switch gears. Instead of going with sodium fluoride, we're going with sodium cyanide. Use the same reasoning. If we want to find out, let's see, the pH of 0.75 molar aqueous solution, we got the Ka for the acid, but we're dealing with a salt. So we actually need the Kb for the cyanide ion. And if we go through and say, these are the major species, similar to our last one. And then we say, these are proposed reactions and throw out the ones that are just stupid. Okay. So we've got to just compare the top two. And we say the Kb is 10 to the minus 5, which is much, much larger than 10 to the minus 14, right? 9 orders of magnitude. So we know that the controlling reaction is going to be the cyanide and water reaction. And then we set up our ice table. It looks just like the rest of them we've always done. Right? Very similar. So there's our Kb and expression, and we're saying that that Kb is so small that the X is not going to be significant, and solve for X, which is the hydroxide concentration. Calculate the POH, subtract it from 14, and you get 11.54 pH. Now, we didn't do the, I don't think we did the 5% rule, but you have to take my word for it. It's kosher.
I'm sorry.
That might be a mistake sometimes. 2 factors control acidity in binary compounds. One is polarity of the bond. If the bond is extremely polar, that means you're shifting, and we're talking about the bond between the hydrogen and some other part of the molecule, right? You can have something else out here, but this part is this bond polar, and we're always talking polarity toward and away from the hydrogen. The stronger, the more polar that bond, the more the strength of the acid increases. You get, it's easier to remove the hydrogen because you're already shifting the electron density away from the hydrogen, and you're giving it a partial plus to begin with. So it just needs a little kick to get a full positive charge and leave the electron behind. So bond polarity, and then bond strength. Low bond strength is good. Now, they may seem like they're similar, and there's some relationship there, but they can be calculated separately. Polarity and bond strength can be calculated separately. And those are what we consider when we're talking about the strength of the acids. We find that bond strength is, if we follow bond strength only for the halo acids, the ones formed from halogens, right? We find that the bond strength decreases toward hydrogen iodide or hydroiodic acid. So it's stronger. This would be the strongest of the bunch right here. This is a little weaker than that one. This is a little weaker. But now you get to the bond strength here is so high that it is, in fact, a weak acid. So that's a quantitative approach. Rather, my explanation earlier with the hydrogen and fluoride was a qualitative approach. This is a quantitative approach. These values have been determined. And by comparison with actual Ka values for these acids, we find that all of these halo acids are strong except for hydrogen fluoride or hydrofluoric acid. Now, other types of acids. Those acids, the oxyacids, those that have the acidic hydrogen attached to an oxygen in between it and another part of the molecule. For example, where we have the carboxylic acids, right? All right, so you got an oxygen between here and something else out here. Or you could have nitric acid. HNO3. I forgot my Lewis diagram. Let's see, 1, 2, 3, 4. Okay. And then a hydrogen here. What's over here? Must be a double bond. No, it can't be. Bad example. Whenever you have an oxygen between the rest of the molecule and your hydrogen, you have an oxyacid. Now, the hydrogen doesn't have to be attached to all of the oxygens. They can be separate. As you increase the number of oxygens, you increase the strength of the acid. So here's the perfect example. If you have, remember when we were naming acids? I started off with this one, the chlorate ion, right? Make an acid out of it. So this is chloric acid, right? Chloric acid. And if we add an oxygen to that one, perchlorate ion, like that, get rid of that. This would be perchloric acid, right? If we go down the other direction, we have chlorous acid, and then keep going, hypochlorous acid. Okay, order these in strength of acidity. That's the strongest. Yep, perchloric is the strongest acid. Now, why is that? Well, you've got, yeah, go ahead.
Oxygens.
Yeah, the oxygens. The oxygen is an electronegative atom, so is chlorine. And the combined effect, and all these oxygens, well, actually, this hydrogen is attached to one of the oxygens in each one, but the other oxygens are drawing electron density away from the chlorine and the hydrogen. And as they polarize that bond further, withdrawing that electron density, they weaken the bond between the one oxygen to which it's attached. And by doing that, they make it easier to remove the hydrogen as you go up with more oxygens attached. So this is the strongest acid of the group. And these are the actual K values. The K value is so large for perchloric acid that we have to estimate it's greater than 10 to the 7th. Chloric acid is about 1, right? So it's nothing to be sneezed at. And you can say the same thing about sulfuric acid versus sulfurous acid. Right? Sulfuric acid is strong with its first proton. Sulfurous acid is weak with its first proton. Right? So this Ka for a polyprotic acid is only for the first proton, whichever one it could be. Nitric acid, right? It has a very large K value. Nitrous acid has a small K value. We removed one of those oxygens. Okay. All right. Am I getting close to this chapter anymore? Oh, okay. All right. So now we're going to look at the effect of electronegativity on the acidity. And by comparison, we need to compare apples and oranges. Right. So if we compare the electronegativities with oxy acids, the effect is the opposite. Right? So if you've got an oxygen between your halogen and the hydrogen, then the more electronegative you go. We go from let's see, iodine. Right. So we're going more electronegative this way. So the strength of the acid increases going up, actually. We throw this one in here just for comparison. What is that? CH3OH. That's methanol. Okay, they just wrote it backwards. Methanol, right? Wood alcohol, the kind that you don't drink. And we find that the evidence for that is Ka for each of the acids. So the one with chlorine in it is the strongest because it's more electronegative. How about, yeah, H, you may have wondered why HOF is not in there. Well, HOF is not in the series because in water it decomposes. It makes HF and hydrogen peroxide. So we can't determine its K, not experimentally. You can calculate it, but that's only an estimate. All right. So what other types of solutions can we form? Well, if we form an aqueous solution from oxides of nonmetals, our examples there are SO2, NO2, and CO2. If we form aqueous solutions with these guys, what do they form? Well, this one forms H2SO3, sulfurous acid. And nitrogen dioxide forms H2NO3. No, it's HNO2. Nitric acid plus hydrogen gas. That's not balanced. Don't hold me to that. And if we put CO2 in water, what does it form? It forms H2CO3, carbonic acid. So if you have an oxide of a non-metal, right, these guys over here, put it in water, it forms an acidic solution. What's the other possibility? Oxides of metals. When you put those in solution, what happens? That's the next slide. Like K2O or CaO, all right, calcium oxide. When you put that in solution, that forms calcium hydroxide. Yeah, calcium hydroxide. So that forms a basic solution. Metal oxides, often called basic oxides or basic anhydrides, form basic solutions when you put them in water. And non-metal oxides form acidic solutions. Okay. Now, I mentioned this one earlier. We got Arrhenius acid-base definition. We got Lowry-Bronsted acid-base definition. Now we've got Lewis acid-base definition. A Lewis acid and a Lewis base can best be understood by comparing them to our Lowry-Bronsted versions. Right. So if we say an acid is a proton donor, so let's just say water. Do that. So we've got this hydronium ion plus, plus the conjugate base. Right. So that's a Lowry-Bronsted acid. So what's happening in here? Well, when that hydrogen leaves, these electrons go here. And that gives us the negative. So Bronsted-Lowry acid is also a Lewis acid, but by a different definition. If this donates a proton here, what has to happen? Electrons have to be transferred to the A. So a Lewis acid is an electron acceptor. Anytime you get electrons accepted, which is what happens to this one, electrons are accepted here. This is the Lewis acid. This would be a Lewis base because it can donate electrons. Okay, so this would be a Lewis acid. This would be a Lewis base. Now, the advantage of this concept is that the reaction does not have to occur in aqueous solution. I just threw this one in aqueous solution, but it doesn't have to be, because now we're talking about electron transfer, and you can do that without water. Okay. I think Lewis acid, Lewis base definition, Lewis came up with this so that we could expand our definition of acidity and basicity into the organic chemistry realm. Because a lot of organic chemistry, a lot of organic reactions have to occur in non-aqueous solutions because water is a reactant. And if water's there, it'll mess up your reaction. It'll give you a side reaction you don't want. So you conduct your reactions in non-aqueous solutions. But you want to account for this acid-base concept, and this is the way you do it. In this case, the electron pair acceptor is aluminum 3+. It accepts electrons from water. I guess we do have an aqueous solution here. From water, and the Lewis base is the electron pair donor. And it makes a bond with aluminum. Makes several bonds with aluminum. Okay. So there's that came straight out of your book by our definitions of acids and bases. Electron pair acceptor is a Lewis acid. Okay, oops. All right, that's just rehashing. Okay, so now we can move on to chapter 15. 15. I'm going to subtitle it buffers, because that's where we're headed. We're headed for buffers. All right. Get that out of my way so I can see it. There are two ways to shift an equilibrium if you're focused only on concentration, right? We've talked about equilibrium in terms of gas pressures and temperatures. But if you're only focused on concentration, there are two ways to shift an equilibrium. One is you can directly change the concentration of the reactants or products. In other words, you can add them to it, or if you've got some way to remove reactant or product, you can affect the equilibrium that way. The second way is you can indirectly change those concentrations by introducing a coupled reaction, a second reaction that does that for you, that either removes or adds reactant or product. Okay, and we did several of those with our last lab. In order to do that second one, where you introduce, well, actually, you can do it either way. This is called the common ion effect, where you have the balanced equation that's in equilibrium, and you shift the equilibrium by introducing or removing one of the common ions in that reaction. If you introduce something to the reaction medium that's not involved with the reaction in some way, either directly or indirectly, then it will not shift the equilibrium at all. So this common ion effect is where our focus should be when we're discussing buffers. This example where we have hydrocyanic acid reacting with water to produce cyanide ion and protons. How could we shift this reaction? Well, if we add sodium cyanide, where's the common ion? Is there a common ion there that we're toying with? Yeah. Sodium cyanide completely dissociates in water or in this solution and produces cyanide ions. And there's cyanide in this part of the reaction right here. So we're adding to the product side. And that shifts the reaction to the left. What should that do to the hydrogen ion concentration or the pH? Well, if it shifts to the left, you're going to reduce the hydrogen ion concentration, correct? Because it's one of the products. And the pH should increase because you're decreasing the hydrogen ion concentration. The balance shifts towards the hydroxyls. It'll become less acidic. Okay. So with that thought in mind, what's a buffer? Well, you can talk about buffers in any number of ways. Buffer by itself just means that a system that resists change. When you impose a disturbance on the system, it will resist change. So you can speak about buffers in terms of electrical circuits. Right? The circuit is buffered. So if you get a big surge of current coming through your line, the buffer will absorb that and reduce the effect. Right? That's what surge suppressors do, that you connect between your computer and the wall, or between the computer and your power supply. But in chemistry, the buffering effect we're interested in is resisting a change in pH. So our buffer solution is one that if we add a strong acid or a strong base to it, the pH won't change much. So some reaction is going on in there. Common ion effect is working to shift the equilibrium in such a way as to minimize the effect of that addition of either acid or base. Now, typically, buffer solutions begin with a weak acid or a weak base, most often a weak acid. So we're going to focus on weak acids, but the same concepts work for discussions with weak bases. And we want in that solution both the weak acid and its conjugate base in the proper concentrations. Because if we add a base, it's going to react with a weak acid. And if we add an acid, it's going to react with the conjugate base. So we got to have both of them in that solution at the same time. Our example here, and it applies to what we're doing today, is the acetate ion. So if we have acetic acid and its conjugate base, it's going to be this plus, and these are all aqueous, so I'm going to write that in. C2H3O2 minus. Okay. We have an equilibrium here. Well, which way is the equilibrium? Well, we know that this K is 1.8 times 10 to the minus 5. There we go. So we know that it's mostly over here. All right. So how would we create a buffer solution so that we could minimize the effect on that term? Well, if we just put acid in solution and we add base, well, let's do first, let's add acid. If we have acid there and we add hydrochloric acid, it's going to get more acid. Right? Because there's the common ion is here and we're adding more of it. So if we add more here, it's just going to move a little bit over here and reduce that some. So it's going to stay acid. And it's going to move acid pretty quick. But if we add base, what's the base going to react with? The base is a coupled reaction, which will react with this one and produce water. So then we'll shift to the right again and replace those hydrogens. Okay. So where is the ideal concentration? That's the question. To create a buffer, you want to not move the pH much. The pH will move, even if it's in its buffer zone, if it's buffer region, the pH will change slightly. If we're interested in a buffer solution, we've got to have the weak acid and its conjugate base, obviously. And if you add a strong acid or a strong base to this, the best way to approach it is 2 steps. One is you take the reaction to completion. Right, so if we add base, we're going to add base to this one. And we're going to say, all right, so all of the base reacts with that and produces a new value for this, and that's 0. And then we do the equilibrium expression from there. We'll come back to that concept in a minute. So we do the stoichiometry first, and then we do the equilibrium. So once we get to this side, then we set it up in equilibrium so that we can go backwards. I think these slides are out of order. It just doesn't seem to flow. Let's do this. On slide 18, skip over to slide 18. I think it'll make a whole lot more sense if we'll come back to this in a minute. Slide 18. Come on. Titration curve. All right, this is what we're going to be doing today, using that reaction. And you're going to take 25 milliliters of a 0.1 molar acetic acid solution. And you're going to titrate with a 0.1 molar sodium hydroxide solution. So this is milliliters of base added. So at 0, right, no base, you're going to have the concentration. This concentration will give you a certain pH. an acidic pH. Let's see, 1, 2, 3, 4, 6, 11, 12. This is pH. So as you add incremental amounts of base, you're going to measure the pH, and that's your data set. You're going to have base added here and against pH. You're going to have values in that data set. And when you plot those, you're going to find out that you start off at a pH a little above 3. And when you start adding base, it reacts with the hydrogen ions and shifts the equilibrium to the right, because you're removing hydrogen ions. The acetic acid now dissociates further to replace those. And you reach a point where you notice the pH flattens out. Right? This is the buffer region. And then at some point down here, it goes like that. And this is equivalence. This volume is the point at which the hydroxyls added equal the hydrogen ions that are available. So you've used up all of your acid at this point. That's the equivalence point. As it turns out, this right in the middle of this stable pH region is 1/2 equivalence. So you've only added half as much sodium hydroxide as required. Now, what does that look like in terms of our equilibrium? What that looks like is, if we start off with a certain concentration here, and we neutralize half of these, that means this concentration is exactly equal to that concentration. Okay, because you've only used up half of it. You've got just as many left over here as you produce over here, because over here, what we've done is we've reacted with that to produce water and shifted this equilibrium over here, but we've only used half of it. Right? So now we have half of the original concentration here, and the other half of it is over here now. So that's the ideal buffer position, where the concentration of your acid is equal to the concentration of your conjugate base. All right? Okay, now let's go back. Well, I actually didn't show that to you, did I? Supposed to be on the next slide. There it is. So that's similar to the plot that you'll get from the data that you're going to collect today. Now I'll come back to this in a minute. Let's go back up here and finish the discussions. Let's see. No peeking. Okay. So how does the buffer work? Okay. If we have a buffered solution where you have equal concentrations here and equal concentration here. So we have X molar there, and we got the same concentration there. You have weak acid and its conjugate base. Right? So what happens when you add acid? If you add acid, that's a common ion over here, right? So you add a reactant and you shift the reaction to the left. So this added acid, hydrogen ion, reacts with the conjugate base until you reestablish equilibrium. Okay? What if you add base? Base is more like a coupled reaction, where you add this base, it combines with that to produce water, and you're removing product. So this shifts to the right to replace that hydrogen. Okay. And by doing so, either way, the concentration of hydrogen ions does change slightly. But because the equilibrium is strongly to the left, then it only produces enough to replace the ones that are needed. So, whether you add acid or base, the pH doesn't change much. Now, I've drawn this relatively flat, but it's only a slight curve. And the best place for your buffer is at this pH right here, because it's got room to go this way, it's got room to go that way. Okay. I'm gonna leave that up there because you need it for this discussion. Henderson and Hasselbalch. Henderson came up with the idea first to look at this acid reaction as a generic form. HA yields H plus and A minus. And if he wants to, and he knows the K expression looks like that. And he also knows if he wants to know the hydrogen ion concentration, he can solve this for hydrogen ions. So that's what he did. And this is Henderson's contribution. He said hydrogen ions are equal to the Ka for the acid times the undissociated concentration divided by its conjugate base. Let's see, I think I've got more discussion there. Yeah, this was in 1908. Around this time, just a little bit after this, Sorensen, in fact, I think it was 1909, Sorensen came up with a pH idea. So Hasselbalch took where Henderson left off and incorporated Sorensen's idea into this equation. Right? So Hasselbalch took that equation and he took the negative log of the entire equation. Okay. Well, that's what it would look like as a negative log. Negative log of hydrogen ion concentration we know as pH. Then the negative log of the Ka we know as pKa. And then the negative log of HA over A minus left it alone because it can vary so much. You don't have to do a log transformation of a quotient, which would be what? If A is divided by B, then log A over B is the same as log A minus log B. So that would be just too far. So he left that part of the equation alone, and we ended up with pH equals pKa minus log of the acid divided by the conjugate base. Well, we don't like negatives. We can get rid of the negatives, we'll do it. So if you change that negative log of HA over A, all you have to do is switch the denominator with the numerator, and now it becomes a positive. So that's a rule from logarithms. So this is the Henderson-Hasselbalch equation. pH equals pKa plus the log of the conjugate base divided by the weak acid. Concentrations at equilibrium. And if you know the pKa and you know the concentrations of the weak acid and the weak base, of course, if they're equal to each other, what does that make that term? Right? It's the top divided by the bottom. Since they're equal, it equals 1, right? And what's the log of 1? 0. 10 to the 0 power is 1. So if you know that you're at this point, this is equal to this, then the pH here is equal to the pKa. Okay? And if you know the pKa is this, all you need is 10 to the minus pKa equals Ka. Okay, because of that mass transformation. If a negative log of Ka equals pKa, then 10 to the negative power of this is equal to that. So once you graph your data and you find out what this pH is right here at the half equivalence, then you can do that transformation, and that will give you your Ka that you compare to the accepted value of 1.8 times 10 to the minus 5. Okay. That's the whole exercise today. So what we also know from the Henderson-Hasselbalch equation is if the ratio of conjugate base to weak acid concentration is the same, no matter what their concentrations are, if the ratio is the same, the pH will be the same. Okay. So I'm running out of time, of course. What's the pH of a buffer solution that's 0.45 molar acetic acid and 0.85 molar acetate? With a Ka of 1.8 times 10 to the minus 5. There's your calculation. Just use the Henderson-Hasselbalch. If you're given that information, right here, these concentrations, we know that these concentrations are there, right there and there. Then you plug those into this equation along with this value, right? Negative log of Ka is the pKa, and we find that the pH is 5.02 for that buffer. Okay. So this just illustrates what happens when you add acid or add base. You shift the ratio slightly, but it doesn't shift the pH very much. Part of that is due to the equilibrium status of our equation, and part of it is due to the mathematical expression. Because pKa is a logarithmic expression, you can change the value quite a bit, and the logarithm won't budge much because it's a power of 10. All right, so for buffer solutions, I've already talked about this. They generally contain large concentrations of the weak acid and its conjugate base. And the larger the concentration, the higher the buffer capacity. That is, the more acid or base it can accept without a pH change. Now, you don't have to remember this one. This is just an expression of buffer capacity. The amount of protons or hydroxide ions a buffer can absorb without a significant change in pH. That's the definition, but this is the, where is it? There it is. That's an expression of the buffer capacity. A change in N. What is N? N is normality. We talked about this before when we talked about concentrations. Molarity versus normality. So if you have a 0.5 molar H2SO4, then it's equivalent to 1 normal H2SO4. Simply because for each molecule at this molarity, you're producing 2 hydrogens. So normality is referencing the hydrogens, not the whole molecule. So the normality change in hydrogen ion concentration divided by the pH change. So the change in normality is how much acid or base did you add? How many hydrogen ions, how many hydroxyl ions per liter did you add? And then what effect does it have on the pH? That's all that beta means. Okay. So how do we choose a buffer? Well, it depends on the pH and the buffering molecule. Every molecule has a different pKa. So depending on where this region is for that pKa, will determine the best place for your buffer. So for this one, the best buffer region is about 4.3, 4.4, 4.6, something in that region. If we want a different buffer region, like up in here, then we'd need a different molecule with a different pK that would give us a curve that puts the buffer in that region. So the short version is when you select your buffer, you select the buffers so that its pKa of the molecule gives you the same, is near the pH that you want to buffer. We want to buffer here, pKa would be there. Okay. Now, if you have a molecule that's got more than one proton in it, like phosphoric acid, right? Phosphoric acid would be something like this, like that, like this. So you have a possibility for a buffer here, possibility there, and possibility there. Remember, since there are 3 different protons, you've got a different buffer reaction here than you do here. So that you focus on the second buffer reaction, the second pK, Ka2, would give you the pH over here, pH there, here. That's why a great many biological buffers, right, that biologists, biochemists use are based upon phosphate, because you have 3 choices to mix up your buffer. For a chemist, you can increase the buffer capacity just through the roof, basically. But for living systems, you have to be careful with having large concentrations of acid and conjugate base, because they can introduce ionic effects and have a detrimental effect on the cell walls, on the DNA, on the biochemical machinery in the cell. So you have to be careful with living systems. But for chemists, we have a little broader available buffer zones. Okay, this is the titration curve I was talking about before. This is the equivalence point, or the stoichiometric point. Now, when we're doing, during the first semester, we were doing determining the molar mass of citric acid, right, by doing a titration. In that case, we only wanted to get close to the equivalence point. So we used a phenolphthalein indicator. And this is in the region of, actually, that it should be a little bit higher, I think, here. So phenolphthalein is going to change between pH 8 and 10. Right. So our equivalence point, as it turns out, is in the neighborhood of 9. So that was a good choice. But for a titration curve, you're measuring pH at incremental volumes of sodium hydroxide to get that curve. So this equivalence point would be approximated by an end point with the indicator. Okay, that's the difference. All right. So we talked about that before. We're not going to labor that one anymore. You can titrate an acid with a base and get a titration curve. Notice that neither the acid nor the base are weak, right? So you're not going to get a good buffer zone. In fact, this part of the curve down here actually would be even steeper than that. So you're not going to get a good buffer using a strong acid. You need a weak acid or a weak base for that matter. But you can run the titration backwards and titrate by adding acid to a known amount of base. Okay, so when we do a titration, it's often useful to do the stoichiometry first. Just treat it as if what you've added has gone to a certain point and it's gone all the way there. It didn't stop in between. That way, that gives you a starting point for the equilibrium part. Then you can set up your ice table from the stoichiometric point and work your way back to the actual pH. That seems to work better than trying to do it from this end as an equilibrium problem. In this problem, we're considering a solution that's made up of 0.1 mole of hydrogen cyanide and 0.04 moles of sodium hydroxide in 1 liter. So both of them are in 1 liter. We know what their concentration is to start with. Yes, in aqueous solution. So let's put what we know up here already. HCnKa equals 6.2 times 10 to the minus 10. And we have 0.1 molar there. And we are going to add to that 0.04 molar sodium hydroxide. 0.04 mole in a liter, so it's 0.04 molar. Okay. Let's ask ourselves, when we put this in solution, what are the major species? Right. Sodium hydroxide completely dissociates into sodium and hydroxyl ions. Water is always there, and HCN is there to begin with. Why? Because it's a weak acid. It's the major species for hydrocyanic acid in solution. Then we look at reactions. Right? There's water, there's hydrocyanic acid with water. They're the ones that, let's see, yes. So those are all possible reactions that we could expect with those species. Right? That one doesn't make any sense because sodium hydroxide is completely soluble. It will not recombine with hydroxide. And sodium ions do not react with water to produce sodium hydroxide again either. So what about these others? Well, we got these three. How do we decide which one controls the reaction? Well, we want to go through the stoichiometry first. Right? So I'm thinking that HCN has to react with the hydroxyl ions. That's the stoichiometry problem, where you have acid reacting with the base. So this one is our stoichiometry. Where you have this major species reacting with this major species to produce cyanide ions and water. Okay. So after this reaction is complete, the major species are not hydroxyl and not HCN. The major species are these two, water and cyanide ion. If we follow the stoichiometry, you've still got sodium in there, of course. We just didn't write it here. And there's HCN. I wouldn't say that HCN is a major species. I'm not sure why that's there. Because after the reaction, we've consumed all the HCN. Now we're going to the equilibrium problem. Right? Oh, this is one of those problems that they lead you up to the edge, but to the trough, but they don't let you drink. All right. So we're just kind of let this one go and go to the next problem. All right. So now we want to calculate the pH when we mix 0.2 moles of acetic acid okay, with 0.03 moles of sodium hydroxide in 1 liter. All right, so now we've got, let's write what we've got up there. 0.2 mole, 0.20 moles per liter, so that's molar, HC2H3O2. And this has a Ka of 1.8 times 10 to the minus 5. Okay. And we also added to that 0.03 moles per liter, molar, sodium hydroxide. Okay. All right. So what are the major species? Sodium hydroxide, acetic acid, and water. All right. So there are the possible reactions, and we're going to eliminate these because they don't make any sense. And then we're going to look at which reaction controls the pH. Well, hydroxyl reacts with the proton donor. And that will be the strongest acid in this bunch, which would be the acetic acid molecule. Right? Because this is a weak acid, so it's going to be primarily that molecule. So the first thing that's going to happen in a stoichiometry problem is that this molecule is going to react with hydroxyl and produce acetate ions plus water. Right? So that should be on the next slide. Right. So if we write it that way, C2H3O2 is going to react with the hydroxide ions and produce C2H3O2 minus plus water. So initially we have 0.2 molar here, 0.2 molar, and we have 0.03 molar here. Let's see, throw away a 0. There we go. And we have nothing over here. Right. So what kind of change are we going to see? And this is the stoichiometry. So all of this is going to be consumed, right? Because it's one of these for every one of those. So all of this will be consumed. And this is not really equilibrium. This is the stoichiometric point. This is going to be 0. This is 1 to 1, so we're going to produce that much of this one, which means 0.030 molar there. And for this one, we're going to subtract this amount, which has reacted with the acetic acid. Right. So what do we have left over? Well, we have 0.170, right? Now 0.17. Yeah, because of that stop there. Okay, so this is the stoichiometry that we work with for the next step, which is the equilibrium. So once we've completed the stoichiometry, now what do we have? Well, now we have a balance between this base, conjugate base, and its acid, because there is some of each in there. Okay. Right. So now we have the equilibrium problem. The equilibrium problem says that this acid, and I'm going to use the abbreviated format. They use the complete. The abbreviated format says this gives us more of that, and C2H3O2. Okay. So what's our starting point? Now, our starting point after stoichiometry for equilibrium is we have only 0.17 molar of acid to start with. And then we don't have any of this, right? Because we've consumed all the this hydroxyl is used up, and in the process, it used up the hydrogen ions from here. So that's approximately 0. And this one is 0.030 molar. Okay. So what kind of change are we going to see? Which way is it going to go? Well, if this is 0, it has to go that way, correct? Yeah, it has to go that way. So now we're gonna add some of this, and then we're going to add the same amount here, because it's coming from over here, like that. And at equilibrium, we have 0.17 minus X, and then we have X here, and then we have 0.030 plus X. Okay? So this is our equilibrium expression, because this relates to that Ka. Okay? So if we write the Ka and we put X times 0.03 plus X in the numerator, 0.17 minus X in the denominator, and we're going to say that this is roughly 0, very small change. So we're approximating, and and that's equal to the Ka. And if we solve for X, we get 1.02 times 10 to the minus 4 hydrogen ion concentration, and the pH is 3.99. And you can do the 5% on your own, but if you want to take my word for it, it meets the 5% rule. Okay, now that's the way we did it, the long way. And sometimes that's the only way that you can do it. But in many cases, Henderson-Hasselbalch will solve this equation for you. So that's what we're going to do next. Once we've gotten to this point, we know what the equilibrium is. Let's see. 0.03. Yeah. Once we've gotten to this point, where we know that this one is 0.03 molar and this one is 0.17 molar, then we can put these values into Henderson-Hasselbalch. This would be the conjugate base, the A minus part. This would be the HA part in the quotient, the log quotient. So that's why we have this one right here, right? There's 0.03, the base. There's the acid. There's the pKa. We have to take the negative log of the Ka and then solve it for pH, and we get the same value. So that's a lot quicker, a lot less painful. Okay, let's see. We've got another one. We'll leave that there and just change a few things. Stoichiometry. Okay. And there. Equilibrium. And let's erase this part. Okay. Now let's see, what are we given? 100 milliliters of 0.1 molar acetic acid. Calculate the pH of 100 milliliters of 0.1 molar acetic acid. That's it. Okay. So we're using this expression, 0.1 here, 0, 0, minus X, plus X, plus X, 0.1 minus X. And we set up our equivalence to the Ka value, which is right here. And then we approximate by dropping the X and solve for X. And we get a pH of 2.87. See. All right, we didn't do Henderson-Hasselbalch with that one, but you should be able to. Should be able to do Henderson-Hasselbalch with that one. No. No, Henderson-Hasselbalch won't work. Why? Let's go back. Henderson-Hasselbalch won't work because we don't know what the base is. Right? We don't know what the conjugate base concentration is. That's part of the calculation. So you have to do this one the long way. Only when we're calculating buffers where we have concentration for the acid, the weak acid, and some concentration for the base, the conjugate base, then you can use Henderson-Hasselbalch. All right, so we got another one. Well, let's see, this is kind of messy. I'm just going to erase this and start over again. We got different, now we're acetic acid again. Okay, so this still holds, but the concentration is different. 100 milliliters of 0.1 molar acetic acid. Like 1 molar, 100 milliliters. Okay. And 50 milliliters of 0.1 molar sodium hydroxide. Okay, that's our system. Let the reaction go to the completion. So the stoichiometry is the first step. And when we react acetic acid plus the hydroxyls yields what? Well, it yields C2H3O2, the acetate ion plus water. And initially, our concentration for this one is 0.1 molar. And initially, the concentration for this one is 0.1 molar, but there are 50 milliliters of this one. And there are 100 milliliters of this one. Okay. All right. And there's 0 of that one. Now, how do we deal with this one? Well, you've got 1 proton for this one. You got 1 hydroxyl for each one of these. So if we calculate the number of millimoles of each, then we can do the stoichiometry. Right, so 100 times 0.1 is 10 millimoles of hydrogen ions. And this one is 50 times 0.1, which is what, 5? 5 millimoles of hydroxyl. Correct? All right. So what's the change? Well, this one we're going to lose all 5 millimoles. And this one's going to be 10 millimoles minus 5 millimoles. Notice here that I'm working with absolute amounts rather than concentrations. And the reason I'm doing that is because it's stoichiometry. Okay, so this one's going to give us 0 hydroxyls. This one's going to give us 5 millimoles of acid, correct? Now, what's going to be on this side? Well, if this disappears, it's 1 to 1. So what we're going to have over here is plus 5 millimoles of that one. So now we have 5 millimoles here, there. Okay, that's the stoichiometry. But in order to do equilibrium, we need concentrations. So we got to reconvert this to concentrations. How do you do that? Millimoles divided by milliliters of total solution gives you molarity. I showed you guys that first semester. So if we divide this by total volume, 150, it was 150 milliliters. Divide this one by 150 milliliters, we'll get a concentration. All right. So 5 divided by 150 is 3. That's not right. 5 enter 150. 5. There we go. This is 3.33 times 10 to the minus 2 molar. And this is coincidental. It won't always happen this way. It's the same, 5 divided by 150. This is also 3.33 times 10 to the minus 2 molar. Okay? So let's see what the slide has to say. Right. 0.033, 0.033. Okay, that's how they got those numbers. Well, this approach is slightly different. What we've done instead of going my route like this, we converted this molarity to this. We changed this molarity based upon the dilution from 100 to 150. So when we did that, we get 0.0667 molar in this acid in solution before the reaction occurs. And this one would be 0.033 molar before the reaction occurs. That works also. Either way works fine. Once you've got the concentrations, then you can work down where this one goes to 0, this one ends up at 0.033, and this one ends up at 0.033. So we get to the same place by different routes. Okay, now that we have those values, right, then for this reaction, well, let's do it this way. Let's be consistent. C to A to the minus and H plus over here. For that reaction, we set up the equilibrium using Henderson-Hasselbalch. We know what the conjugate base concentration is. We know what the acid concentration is left over. So we plug it in the Henderson-Hasselbalch equation, and we get a pH of 4.74. All right. Okay, this one's a little more complicated because now instead of a weak acid, we're using a weak base. So let's clear the board. So we want to know pH of the solution made by mixing 100 milliliters of 0.1 molar ammonia, which has a Kb of 1.8 times 10 to the minus 5. Anything look strange? The Kb of ammonia is 1.8 times 10 to the minus 5. The Ka of acetic acid is 1.8 times 10 to the minus 5. Remember what we studied earlier? If the Ka and the Kb are equal, then if you take the salt put that in water, it's going to be a pH of 7 because the Ka of this one equals the Kb of that one. Okay, there's an example of equal K values. Okay, that wasn't part of the problem. I just thought I'd bring that up. Okay, we've got ammonia and ammonium chloride in solution. Okay, we want to calculate pH. So we've got 100 milliliters of 0.1 molar, 0.1 molar ammonia, and with a KB of 1.8 times 10 to the minus 5. And we have 50 milliliters of 0.1 molar ammonium chloride. Okay. So how do we reconcile those two? Well, the stoichiometry, that we set up, when these go into solution, we've got a situation where ammonia in solution could react with water and produce ammonium plus hydroxide. Okay. If we just put this ammonia in water, just this in water, then it will make that reaction. Instead of that, we've actually created the solution with part of this common ion right here. Okay, so in this stoichiometry part, what's the concentration of ammonia? Well, it's 0.1, it's 0.1 moles, initial 0.1 molar times 100 milliliters is the number of milliequivalents, and the total volume is 150 milliliters. So the molarity here is that 0.66. Excuse me, left out a 0.667 molar. And the concentration of this one by the same method, right? 0.1 molar times 50 milliliters is the number of millimoles divided by the volume, which is the same, 150 milliliters. Now, why 150? Because we put 100 milliliters of this together with 50 milliliters of that, makes a total volume of 150. So this initial concentration is 0.033. Okay? So what's the change? Well, which way is it going to go? At this point, we've got 0 hydroxyl, so it has to go to the right, correct? So we're going to lose some of this. We're going to gain exactly the same amount of that and gain there. So this is stoichiometry. Right? At stoichiometry, we get 0.0667 minus x, and this is 0.0333 plus x, and this is plus x. Okay. And that's the same. That's what we had on the previous slide. Now, what's the KB? You know what? This is the equilibrium, right? This is the buffer, because we've got the weak base and its conjugate acid. Yeah, this is the buffer. So what does the KB represent? The KB represents this times this divided by that. Right? And that's what this first part says. That's KB, where you react the base with water. and you get the conjugate acid plus hydroxyl. So we put the conjugate acid and the hydroxyl up here, and then we put the base here. And we assume that X is going to be very small, so that's approximately that. We solve for X, and what is X? X is hydroxyl concentration. Right? So why don't we just take the negative log of hydroxyl and subtract it from 14, and we get a pH of 9.56. And I already checked the 5%, and it does pass the rule. Okay, or we can use Henderson-Hasselbalch. The thing about Henderson-Hasselbalch is it's written for Ka and conjugate base over acid. So that's where it gets tricky using a weak base in the Henderson-Hasselbalch equation. So if you get your values correct, right, if you get this one here, the equation is now written in form of the acid reacting with water. We just sort of inverted it. So what's the concentration of ammonia? Right, it's this one. What's the concentration of the base? This one. Okay. Now with that, what we need to do is convert the Kb into a Ka. Right, so we just used our Ka equals Kw, or 10 to the minus 14 divided by Kb. That gives us the Ka. Now we can use Henderson-Hasselbalch. So the Ka is 9.25 for this reaction. Right, you have to write it correctly. We don't have the base on this side anymore. We have the acid. Then we plug those values into Henderson-Hasselbalch with ammonia on top, because it's the conjugate base now, and NH4 plus is the acid. And we put those values in their correct position, and we get a value of 9.56, which is the same as before. So you can use Henderson-Hasselbalch for base reactions as long as you make the conversion to acid format so that it fits the Henderson-Hasselbalch, all the premises that are involved in that equation. Okay. Calculate the pH of the solution by mixing 1 liter of 0.5 molar ammonia with that Kb and 0.5 molar ammonium chloride solution, then by adding 0.1 mole of HCl gas. Okay. Why did we do that as a gas? Because we don't want to change the volume. We want to get hydrogen chloride in solution, hydrochloric acid, but we don't want to add extra volume. That would complicate the problem. Okay, so I'm going to leave that there. And that equation still works. But what we need is how many moles of ammonia do we have initially? All right. Let's see, we have 1 liter of 0.5 molar ammonia. So we have 1 liter of 0.5 molar ammonia. And we have, let's see, 0.5 liters of 0.1 molar, a half liter, 0.5 liters, correct? 0.1 molar here. Yep. And then we add 0.10 mole of HCl gas. Okay. The reason we're finding out absolute amounts is because the hydrogen chloride was added as a molar amount. So it makes more sense to calculate how many moles of this do we have to start with. Initially, we have 1 times 0.5, or 0.5 moles of ammonia. Okay, And we have ammonium as 0.05, right? Oh, no, excuse me, 0.5 times, oh, excuse me. Wait a minute. That's not right. I think there's a typographical error. This should be 0.2 molar ammonium chloride. Okay. Here we go. Point 0.2 molar ammonium chloride. So that would give us 0.1 moles of ammonium. No, it wouldn't. 0.5, 0.2. Let's see, 1/10 of this would be, yeah, that's right. 1/10 would be 0.05, 2/10 would be 0.1. That's right. That's right. So we got 0.1 mole of ammonia initially. Okay. Then we're going to add 0.1 mole of HCl. So let's see what that does to it. Okay. All right. So we got that one reversed. We're not actually doing it this way. We're doing it the other way. So this would be hydrogen ions. So this would be ammonium 0.1 mole here. Okay. This is the stoichiometry. Right, so that's before, this is after. So this is going to be consumed in producing that. So this goes to 0. And this one goes to 0.4 mole. Correct? And this one, we actually add 1/10 of a mole. There we go. So this is the point where we start equilibrium. That should be on the next slide. Yeah, we need to calculate the concentration of base and acid. So this is, let me remove that. We're going to use Henderson-Hasselbalch. So we got 0.4 moles, and what's the total volume? 1 liter, 1.5 liters. 1.5 liters. So this concentration is going to be 0.267 molar. And this concentration is going to be half that, 0.133 molar. There we go. So now that we have the base and the acid, we can use Henderson-Hasselbalch. We just have to be sure and use the correct K value, which is there. We calculated again, 5.56 times 10 to the minus 10. And then the pKa is 9.25. Now we can plug it into the equation, just like we did before, with the proper base on top, acid on the bottom. Okay. Let's see. All right. So let's do a titration. What's the pH of a solution at the equivalence point? Okay. The equivalence point in an acid-base titration will not always be 7. If you use sodium hydroxide and hydrochloric acid, 2 strong acid base, then yes, the equivalence point will be at 7. But if you've got a weak acid and a strong base titrating, the mixture is going to tend toward the basic. Right? Remember when we were talking about equivalent amounts of weak acid and strong base will give you a basic solution. Well, the equivalence point is going to be in the basic region. Right? So we know that right off the bat. All right. If we're going to calculate the pH at equivalence, 100 milliliters, 0.1 molar acetic acid. 0.1 molar acetic acid. Okay. And we're going to titrate that with 0.1 molar sodium hydroxide. Titrate to equivalence with 0.1 molar sodium hydroxide. Okay. And the Ka for this is 1.8 times 10 to the minus 5. Okay. So at equivalence, since these concentrations are equal, 0.1 and 0.1, then at equivalence, we need the same number of moles of hydroxide as hydrogens, which means you need the exact same volume. So at equivalence, this is going to be 100 milliliters of sodium hydroxide solution. Right? We know that right off the bat. So the total volume is going to be 0.2 liters. 100 milliliters plus 100 milliliters is 200 milliliters, which is 0.2 liters. So we know the concentrations of each one before the reaction. And I'm not going to put it on the board because it's right here. 0.05 molar. We take 0.1 molar acetic acid and we dilute it twice, right? We take this much and add the same volume to it. So we cut it in half, 0.05 molar. We do the same thing for the base. And we know that the reaction is going to the right, right? Because we don't have any. We don't have any acetate ions to begin with. But the reaction is going to consume both hydroxyls and acid. So the stoichiometry is going to leave us with 0.05 molar acetate in solution. That's it. There's no acid, there's no hydroxyl left, just the acetate. Okay, so now we know that the acetate, if it's going to reach equilibrium, the only thing acetate can react with is water. There's no base left. It doesn't react with sodium, right? We write it that way, sodium acetate, but they're separate ions. So that strong conjugate base, acetate, is going to go looking for protons, and it's going to find them at water. So that reaction, acetate plus water, yields the acetic acid plus hydroxyls. That's the equilibrium situation. Okay, and we know the reaction's going to the right because there's no acetic acid left at the end of the titration. So we have 0.05 minus X for the acetate, and we have X for the acetic acid and X for the hydroxyl. Okay. So if we're going to use the base equation, the base reaction with water, we need the Kb So that's where we divide 1.8 times 10 to the minus 5 into 1 times 10 to the minus 14, and we get our KB as 5.6 times 10 to the minus 10. Okay. So the KB here becomes 5.6 times 10 to the minus 10 for that reaction. Okay. And we're going to set up the equilibrium with set up the equilibrium with our two x's in the numerator and our 0.05 in the denominator, because x is very small, and solve for the OH. X is OH. So we calculate POH and subtract it from 14. And the pH is 8.72. So that will be the pH at equilibrium. So today during lab, when you titrated acetic acid with sodium hydroxide on that steep part of the curve, right, milliliters of base and pH, started off here, you went like that, like that. This pH right here at equivalence, by calculation, should be 8.72. Okay? That'll get you in the ballpark if you're looking for it. And then once you find that, assuming your data is good, then you drop down here, and this is the equivalence volume, and this is half equivalence. And that's what you use to confirm the pKa. All right. Now, these are other titration curves with sodium hydroxide against different weak acids. Now, we don't identify which of the weak acids we're looking at. We only identify them by their Ka values. So what you'll notice is for 10 to the minus 5 for acetic acid would be right in here somewhere. So it'd go up like that, and then it'd be somewhere in here. But they all end up at the same place, at the same volume at equivalence. But you'll notice that the smaller the Ka value for the weak acid, the more basic the solution is at equivalence. That's what we get out of that slide. This titrates ammonia with hydrochloric acid. And the equivalence point is still in the steep part of the curve, but the steep part of the curve now is going the other direction. Okay. This would be a titration curve for phosphoric acid. It has 3 buffer regions and actually 3 equivalence points, right? The first equivalence point here is the equivalence for the first proton. The second equivalence point is the volume required to neutralize the second proton. And the third equivalence point neutralizes the third proton. This one doesn't curve up as much as I expected it to. But supposedly this is from real data, so I have to go with it. But this one also has 3 buffer regions, right? The first buffer region is down here at about pH 2.16, right? You see it right there, 2.16. The second buffer region is 7.21. Okay. And the third buffer region is 12.3. All right. So let's talk a little bit about indicators. If we're going to use a color change of an indicator for our titration, right? We don't want to have to go through and titrate every sample and get a curve for each one to find its equivalence point. It's a lot quicker if we have a color change indicator that switches colors somehow very near the equivalence point. That's the end point. But we need to choose our indicator wisely. So how do we choose that indicator? We need to understand how indicators operate. An indicator is usually a weak acid. Right? So the indicator is undergoing its own equilibrium at the same time as the titration is proceeding. The difference is that you only need a tiny amount of the indicator, and it has a very strong color change evident when it reaches its endpoint, its equivalence point, excuse me. Well, let's proceed. Let's see. Yeah, okay. We're going to use phenolphthalein as an example, right? We know that if the solution is acidic, the color is going to be clear. And if it's basic, it's going to be pink. When does this occur? Well, if we look at indicators as an acid equilibrium, right? So they have a proton, and then they have the rest of the molecule, the indicator part of the molecule. And it's in equilibrium with this dissociation. Like that. Okay? When we've got sufficient number of protons in solution, drives the reaction back here and increases this concentration. And once it reaches a certain amount, then we can't see the pink anymore. So it depends on which way the equilibrium is shifted based upon the acid-base environment as to which one we see. Now, to be sure, there is a strong element of physiology involved here. Can we detect the color change? When can we detect the color change? The ratio of these concentrations determines when we can see the color change. And there's a rule of thumb for that. Right? So the Ka for this reaction is equal to hydrogen ions times the indicator, right, divided by the undissociated indicator. And that value for phenolphthalein is 3.98 times 10 to the minus 10. Okay. And the pKa for that, we'll just go ahead and put it up here. Negative log of that value is 9.4. Okay. And you don't have to memorize these. Those are pictures of the molecules. Right? So what it's saying is when there's enough hydrogen ion being added to the solution, it shifts to the left-hand side, and that's colorless. But when we add hydroxyl and we shift away from the acid form to the In minus form, then this system of single and double bonds, which we studied last semester, this is a conjugated system. It drops the absorption profile of the molecule into a region that gives us a visible color. Okay. All right. So there we are again. And here, that tells us that at pH 9.4 is when we get a balance between those two. species, both the protonated version, the clear one, and the pink one, the non-protonated version. So when can we detect those? As it turns out, the human eye can only detect a difference in concentration of plus or minus 10%, 1 to 10. In terms of Henderson-Hasselbalch, the base divided by the acid. This ratio has to be either 1 to 10 or 10 to 1. If it's 1 to 10, the solution appears to our eyes clear. But if it's 10 to 1, it appears to our eyes pink. Okay? So that's when we calculate that as this is 1/10, 0.1, and this is 10. So what power of 10 gives you 0.1? Well, it's 1, right? This is 10 to the minus 1. So this would be minus 1, and this would be plus 1. So this one would show us 10 to the first power would be plus 1. This would be minus 1. So the pH range is pKa, or 9.4, plus or minus 1. That means it goes from 8.4 to 10.4 in order for us to see a pH change. Now, it seems like a lot, but since the pH scale is logarithmic, this massive change between 8.4 and 10.4 doesn't affect the stoichiometry of the problem that much. All right, so when we pick an indicator, we want one that has a pKa in the region of the equivalence point pH. So for acetic acid, the equivalence point was, what was it, 8 point, I think it was 8 point something. Let me look. Just a second here. 8.72. So our acetic acid, C2H3O2, equivalence point was 8.72, right? And the range is 8.4 to 10.4. So since we're coming up from the acid side and going to the base side, then this 9.4 is a good choice. It's just a little bit above 8.72. Okay? It depends on which direction. Are you coming from the acid side or the base side? If we were coming from the base side and titrating something, we would want to use the higher end as our change point. All right, this is a list of indicators. So you don't have to do all these calculations, right? This just proves, and this is how this table was constructed based upon the comparison of these values and some practical application. So this gives you the pH range for color change, and some of them have multiple color changes, right? Which means they might be applicable in different pH ranges, right? Those second and third ones, the cresol red and thymol blue, have color changes in 2 different regions, right? So they must have more than one proton involved in that color change. They must be diprotic indicators. Phenolphthalein, you'll notice, is down around, let's see, it's down around here. Phenolphthalein right here. So this is the range right? Where the indicator is useful. All right. So all you have to do is just find out, all right, at what pH is my titration going to change, is going to reach the equivalence point, and then go find an indicator that works in that region. And then once you've done that, you can use that indicator if you've got 100 titrations to do to determine the concentration of your unknown. Then you can do them like that using your color indicator rather than trying to draw a curve for each one. All right, I think that's the last slide. Yep. Okay, we're done. Next Tuesday, we'll have a review on chapters 14 and 15. And then that Thursday, we'll have an exam. Now, let's see. I don't think we have a lab on that day, though. Let me check to be sure. No. All right. So next Thursday, we're going to have an exam on this material. Right. Next Tuesday, we'll do a review. Thursday, we'll have an exam. No lab on that day. Let's see. There we go. And then the right after the exam, we'll cover the chapter 16. 16, yes. Yeah. Solubility in complex ion equilibrium. And there'll be plenty of time to do it because we won't have a lab. So we can finish that in one day. And then the following Tuesday, we'll have a review. Let's see. Following Tuesday, we'll have a review. Yes. No, we won't. The following Tuesday after that is July 4th. We won't meet on that day. So just to rehash, next Tuesday we review chapter 14 and 15. Following Thursday of next week, we have exam 4 and we'll cover chapter 16, solubility in complex ion equilibrium. Then the following Tuesday is a day off. And then we'll pick it up on that Thursday, July 6th. We'll do a review on chapter 16. And at that time, we will also have lab number 5, our complex ion lab. So you need to get a copy of the lab no later than a week from today. Right. If you come to class, I'll hand them out. If you're not in class, then since we won't have a lab that day, a lot of you probably won't be in class. So you have to get that off of Brightspace. All right.